Hi, my name is Matt Dionis, and I'd like to welcome you to Building Data Visualizations with D3 and Angular 2, Installation and Setup. In this brief section, we will lay the foundation for our Angular 2 app by installing Node.js, installing project dependencies using NPM, establishing configuration settings, and building a very basic Angular 2 component. By the end of this section, we will have an Angular 2 app up and running in our browser, which automatically refreshes anytime we make changes to the code. In this first video, we will learn about Node.js and NPM, and how they will help us build Angular 2 applications. Node.js is a JavaScript runtime built on Google Chrome's V8 JavaScript engine. Node.js has become a very popular choice as a web server for JavaScript developers over the last several years, as it allows one to write server-side code in JavaScript. There is much to be learned about Node.js, but in this course our main interest lies in NPM, which is a package manager that is included in the Node.js installer. If you do want to learn more about Node.js, I encourage you to visit nodejs.org and take a look through the documentation. Let's install Node.js and NPM now. Simply navigate over to the download section of the Node.js website. I recommend sticking with the default installation, which is LTS. LTS stands for long-term support and simply means that you can expect long-term stability, reliability, performance, and security with this version of the Node library. Choose the correct installer for your operating system, most likely Windows or Mac. After the download has completed, find and open the Node package. Now simply walk through the install process. Feel free to pause the video now until Node is installed. The good news is that NPM was automatically installed with Node.js, so we should have everything we need now. Now let's open a terminal window and run a couple basic commands to make sure we have the correct version of Node and NPM installed. Simply type node-v and hit enter to display the version of Node you have currently installed. I currently have version 5.10.1, but any version of at least 4.0.0 will work fine for our project. Now type npm-v and hit enter, and you will see the current version of npm you have installed. I have version 3.8.3, but again, any version of at least 3.0.0 is fine. We will be making heavy use of npm throughout this course for common tasks such as installing project dependencies, starting our app, and running unit tests. To learn more about NPM, visit npmjs.com. Contrary to popular belief, NPM does not stand for Node Package Manager. In fact, it is not an acronym for anything, although the website has fun with some wacky possibilities. Nap power maximum, nothing prevents misery, naturally produced modules. We now have the tools we need to begin building our Angular 2 application. In the next video, we will use NPM to quickly install all of our project dependencies. Welcome to the app configuration section of Installation and Setup. In the previous video, we learned about and installed Node.js and NPM. In this section, we will be setting up our configuration files and using NPM to install necessary dependencies. We will begin by establishing configuration for common development tasks and listing dependencies in package.json. We will then configure settings for our module loader, system.js. Finally, we will add tsconfig.json and typings.json so we can write our app using TypeScript. Note that our configuration will mirror that of the official Angular 2 Quick Start. This way we are staying consistent with the way the Angular team suggests setting up an application. Let's get started. First, let's create our project folder. Open up a terminal window and enter mkdir d3-angular2-app to create a folder for our app, followed by cd d3-angular2-app. to navigate into this new folder. Now open up the text editor or IDE of your choice so we can begin adding some important configuration files to our project. A quick aside with regard to text editors and IDEs. We will be writing Angular 2 in TypeScript in this course, so I highly recommend choosing an IDE with support for TypeScript to get all of the benefits such as rich IntelliSense. I personally use Visual Studio Code on a daily basis and will be using it throughout this course. You can download VS Code from code.visualstudio.com. A couple other great options are Sublime Text or WebStorm. Create a file in the D3 Angular 2 app folder called package.json and add the following code to it. This code is available in the course materials. Let's walk through package.json now so we have a better understanding of what's going on in this file. The first fields you'll notice at the top of this file are name and version. These are required fields in any package.json and set the name of our project, D3 Angular 2 app in this case, and the version, 1.0.0 for us since we're just getting started. Below this are some helpful scripts, which are run using npm. These scripts execute tasks such as starting up our project, watching TypeScript files for changes and transpiling, and installing typings files after we run npm install. Further down in package.json, you will find a list of dependencies and dev dependencies. These are libraries which our application will depend upon, such as Angular core libraries, the Angular router, and system.js. We will use npm to install all of these dependencies at the end of this video. The next file you'll need to create is system.js.config.js. System.js is a module loader which directs our app where to look for packages and dependencies. For example, within the map object, you can see that all Angular files are located in node modules/Angular. There are alternatives to System.js available, such as Webpack, but in this course we will be using System.js as it is the module loader the Angular 2 documentation currently uses. You can learn more about System.js through their GitHub page at github.com/systemjs/systemjs. We will be writing our Angular 2 app in TypeScript in this course. TypeScript is a superset of JavaScript which is transpiled into JavaScript. TypeScript gives you the option to write strongly typed JavaScript and to use all of the latest JavaScript features found in ECMAScript 2015 and beyond. If you would like to learn more about TypeScript, visit typescriptlang.org. In order to use TypeScript in our project, we will need to set up some basic configuration in two files. The first file is tsconfig.json. We won't be spending time diving into this file. All you need to know for this course is that this file is required and that it teaches the compiler how to transpile TypeScript into JavaScript. The next file is typings.json. This file provides the TypeScript file with definition files for libraries we will be using such as Node, Jasmine for testing, and Core, which provides us with ECMAScript 2015 and ECMAScript 2016 capabilities. Now we will install all the dependencies we declared earlier in package.json. To do so, simply open up a terminal window, make sure you are in the D3 Angular 2 app directory, and type npm install. This command installs all of our dependencies. A quick tip: you should now see a typings folder in your project directory. If you don't, simply run npm run typings install. We have now created a project folder, added our configuration files, and installed all necessary dependencies. In the next video, we will begin writing code and building our Angular 2 application. Welcome to the final section of installation and setup, where we'll get our app up and running in the browser. In the previous video, we set up our app configuration and installed all necessary dependencies, which means now it's time to start writing some code. We will begin by creating our first Angular 2 component and bootstrapping our application. Next, we will set up our index.html and add some basic CSS styles. Finally, we will revisit our old friend npm and use it to get our app up and running. We will finish off this section by testing our first Angular 2 app live in the browser. First, let's jump over to our terminal window. Make sure you are in the root of the D3 Angular 2 app directory and type mkdir app to make an app subfolder within D3 Angular 2 app. All of our Angular 2 code will live within this new folder. Our first component will be very basic. First, we import any modules or libraries we need. In this case, it's just one, Angular core, which you may remember seeing earlier as a dependency in package.json. We need this module so we can gain access to the component decorator, which we will make use of now. We associate metadata with this decorator in order to tell Angular how to create and use our component. We specify which CSS selector this component will be tied to, and also attach a very basic HTML template. Next, we declare our component class. Note that this class is empty, as this first component is very basic. We will be adding much more to future component classes we create throughout this course. Pay special attention to the word export. We export this class so that other pieces of our application have access to them through importing. We now need to set up the root module of our application. Every Angular 2 application needs a root module. Every app which runs in the browser will also require two Angular modules, ng module and browser module, which we import here. We also import the root component of our app component, which we just created. We now need to supply metadata to the ng module decorator function. We declare any other modules that our root module needs, here simply browser module. We list all components and directives that belong to this module in the declarations array, here simply app component. We also declare app component in the bootstrap array to identify the root component of our application. Now it's time to bootstrap our application. Create a new file within the app folder and name it main.ts. Once again, we will make use of the import statement. This time we have two modules to import. First is an Angular module which helps our app bootstrap in the browser. The other import is of the app module, which we just created. We finish this file off by calling the bootstrap module function of platform browser dynamic and passing in our app module. When our app loads, it will call this function and look through the metadata of app module to know how to set up our app. However, currently, it would not be able to find this component selector in the HTML. Let's fix this. Create a new file in our project's root folder outside of the app subfolder and name it index.html. Copy the following lines, which are available in the course materials, into this file. The top of this file simply declares necessary JavaScript libraries and sets system.js configuration. The most important line to focus on is where we declare the D3 app selector. Thanks to our app component, Angular knows exactly what to do when it encounters this selector. Let's add some basic styling to our HTML. Create a file in the root of our project and name it styles.css. If you take another look at the top of index.html, you'll see that this file is already referenced there. After adding these basic styles, we are ready to start our app. Jump back over to the terminal and type npm start. We defined what this command does in package.json earlier. npm start starts up our app, runs the TypeScript compiler in watch mode to watch for any changes as we write our TypeScript, and also refreshes the browser anytime our files are updated. We now see our app up and running in the browser. In installation and setup, we learned about Node.js and NPM, configured our Angular 2 app, and got it up and running in our browser. We now have a basic Angular 2 app and everything in place to begin adding D3 and building out a much more interesting application. Welcome to Building Data Visualizations with D3 and Angular 2. My name is Matt Dionis, and I am a self-taught developer. One of the most beneficial tools I used while learning how to program were video courses similar to this one. I am excited to give back to the community by teaching and hope to inspire others to pursue a rewarding career in development. I spend most of my time working with JavaScript and JavaScript frameworks and libraries, specifically Angular, Angular 2, D3, and Node. I'm fortunate enough to work with the incredible team at Circle, where I help build internal tools. Visit circle.com to learn more about the exciting apps and services we are building. I can be reached on Twitter at MattDionis, and I encourage you to reach out with any and all questions, comments, and feedback. In this brief section, we will lay the foundation for our Angular 2 app by installing Node.js, installing project dependencies using NPM, establishing configuration settings, and building a very basic Angular 2 component. Now, for a sneak peek at what we will be building in this section, we will begin by learning how to import JSON data using D3 functions. We will then attach this data to elements within the document object model, more commonly known as the DOM. Next, we will use SVG to build a basic bar graph. Finally, we will customize this bar graph by adding interactivity, setting the color, setting a scale and attaching axes, and adding some basic labels. In this section, we will briefly discuss D3 mapping. Next, we will gain an understanding of both GeoJSON and TopoJSON data. We will then learn how to use command line tools to produce TopoJSON files. Finally, we will use D3 to style a choropleth map based on TopoJSON data. In this section, we will add a legend to our map. Next, we will add some basic interactivity in the form of zooming. Finally, we will learn how to add custom tooltips to our map. In this section, we will begin by discussing modularity in Angular 2 apps. Next, we will tackle components and their importance within Angular 2 apps. After this, we will discuss data and event binding. We will then go over services in Angular 2. Finally, we will wrap up this section by discussing unit testing in Angular 2 applications. In this section, we will begin by introducing Angular CLI, which makes creating a basic Angular 2 app very easy. Next, we will work with structural directives and class bindings to make our template more dynamic. We will then review creating services as well as mock data. Next, we will introduce Angular 2 forms and add one to our app. We will then discuss adding routing to our app. Finally, we will wrap things up by writing some unit tests. In this section, we will begin by discussing our Node.js, specifically Express, server. We will then learn how to import D3 into our Angular 2 app. Finally, we will learn how to use D3 to display data in real time. In this section, we will make use of the input decorator while building a tweet component. We will then begin using D3 as we build a scatterplot component. We will continue to use D3 as we build a map component. Finally, we will add some basic interactivity and animations. Welcome to the second section of Harnessing the Power of D3, where we will be building a bar graph with D3 using JSON data. We will begin by learning how to import JSON data using D3 functions. We will then attach this data to elements within the document object model, more commonly known as the DOM. Next, we will use SVG to build a basic bar graph. Finally, we will customize this bar graph by adding interactivity, setting the color, setting a scale and attaching axes, and adding some basic labels. In this first video, we will learn how to import JSON data. We will set up a very basic page and add a reference to the D3 library, work with JSON data, then import JSON data and begin working with it. First, let's jump over to our terminal window, creating a folder for your bar graph called D3 bar graph by typing the following on the command line: mkdir d3-bar-graph. All of our code for this section, including an index.html file, JSON data, and our JavaScript file, which will contain most of our code, will live in this folder. Now open up the D3 bar graph folder in your text editor or IDE. Within this folder, create a new file and name it index.html. This file will be where we reference all of our necessary resources and files such as the D3 library. We will also set up the div which will hold our D3 visualization here. Add the following code to your index.html file. This file is available in the course resources. This file is very simple at this point as it simply sets up an HTML document with a title D3 bar graph, a reference to the latest D3 source code, and a reference to our bar graph JavaScript file where all of our D3 code will be written. We will be working with the latest release of D3 in this course, version 4. D3 v4 is much more modular than previous releases of D3. This means that you do not need to download or reference the entire library if you only need certain modules within the library. For example, if you only needed to work with D3 axes functions, you could simply download or reference the D3-axes module. Throughout this course, we will make use of many different modules within the D3 library, so we will simply reference the entire library. The reference to bargraph.js at the bottom of the body points to our future D3 code. Let's add this file and begin writing some code. Add bargraph.js to the D3 bargraph folder and open up this file in your text editor. It's now time to write our first line of D3 code. Let's start by using a D3 selector to grab our body element. You will find that D3 is a very semantic library. So D3.selectBody does exactly what it sounds like. It selects the body element. Add .append h1 to this line to append an h1 element. Finally, add .text let's build a bar graph to this line. Save this file and open index.html in your browser. You should see let's build a bar graph in your browser. We have just successfully written our first D3 code. Now let's follow the message printed on the screen and begin visualizing some data. Replace the contents of bargraph.js with the following code, available in the course resources. For our bar graph, we are going to use a hypothetical data set covering daily sales at a lemonade stand. Let's work with some D3 functions to display this data on the screen. We begin by typing d3.select body.selectAllP. We learned earlier that this chain of functions will use D3 to select the body element and select all to select each p or paragraph element. But wait, we don't have any paragraphs in our HTML. That's true, but we soon will once we import our data. Type the following lines: .data, sales data, .enter, .append, p. .data of sales data uses the D3 data function to pull in our sales data. .enter begins to describe what we will do when each piece of data, each member of our sales data array in this case, is encountered. Finally, .append p declares that we want to use D3 to add a paragraph element to the body for each member of the sales data array. We now should have 7 paragraph elements within our body, 1 for each day of the week. However, if we were to view the page in the browser, we would not yet see anything. We first need to add some content to these paragraphs. Add the following line after .append p. .text, function of D, which is the element of data from our sales data array. Then return this string, where we append d.day, which is that data element's day property. Bestseller was d.bestseller. There were d.sales, total sales. This line simply uses the D3 text function to set the contents of each paragraph. The function within text takes a first parameter which maps to the data we have imported. In other words, D represents each member of the sales data array. Let's save this file and view it in our browser. We now see a sales summary for each day of the week. We currently have our data hard-coded within bargraph.js. However, this is not how one would build a production-ready application. Let's make a few changes so we can properly import our JSON data from its own file. First, we will need to set up a very basic server for our page to function properly. Otherwise, our browser will throw cross-origin errors when we attempt to import JSON data from a separate file. On the command line, within our project folder, D3 bargraph, type python-m simple HTTP server. This will set up a very simple local server. You can now reach your page by navigating to localhost:8000 in the browser. Note, you will see the port number on the command line. If it's not 8000, simply navigate to whatever it happens to be. For example, localhost:3000. Your page should look and feel exactly the same, but now we can safely take advantage of D3's ability to import JSON files. Open up bargraph.js and make the following changes. Remove the sales data array. Update the D3 code to the following. The D3.json function is used to import JSON data from an external source. This function takes a callback function, which runs after the data has been imported. The contents of this function should look familiar, as the code is the same as previously. We now simply need to create the salesdata.json file. Create a new file called salesdata.json and paste the following JSON array in. This again is available in the course resources. Saving this file, refresh your browser, and you should see the same list of paragraphs, but we are now pulling data from a separate JSON file. In the next video, we will use the same dataset to build and style a bar graph. Welcome to the second video of Harnessing the Power of D3, where we will be building and styling a bar graph. We will begin by building a very basic bar graph and properly positioning it. We will then style our bar graph by adding custom colors, animated transitions, and basic interactivity. Our bargraph.js file currently looks like this. We are displaying a short paragraph, 2 sentences, for each day of data in our salesdata.json file. We would now like to instead display each day as a bar within a bar graph. To do so, we are going to work with something called SVG. SVG stands for Scalable Vector Graphics and is a text-based image format. SVG is XML-based and uses markup code similar to HTML. One of the great benefits of SVG is that it is infinitely scalable, meaning it will look excellent on any size device. So now that we know a little about SVG, let's begin using it. First of all, we need to create an SVG canvas which will hold all of our SVG elements. Let's choose a width, height, and padding for this canvas. We will go with a 400 pixel width, 300 pixel height, and a padding of 100 pixels. We can set this canvas up with the following code. We select the body, append our SVG canvas, and set its width, height, and padding to the values we set above. Now let's view our canvas in the browser. Refresh your browser and you should see a large blank area at the top of the page. This area holds our SVG canvas. To prove this, simply right-click in the area and click Inspect. You will see an SVG element with width 400 and height 300 in your HTML source. Now let's add our bar graph to this SVG canvas. We will now replace the code that was within the callback function of d3.json. In order to build a bar graph, we need to append rectangles to our SVG canvas. To do so, we begin by writing svg.selectAllRect.data.enter.append.rect. This should look familiar. We are selecting all rect elements within our SVG canvas, of which there are none at first. We're setting the data to the data returned by our callback from D3.json salesdata.json. Then we use .enter.append.rect to append a rect element for each object within our data array, each day of the week in our case. A rect element always needs 4 attributes: an x value, which is where the rect begins on the x-axis, a y value, which is where the rect begins on the y-axis, a width attribute, and a height attribute. We will set these attributes with the following code. If we save this file and refresh our browser, we will notice something fairly disappointing: just one black bar. If we inspect this bar, we'll notice that it's actually 7 bars, one stacked on top of the other. This makes sense if we think about it. Our code currently appends a rectangle for each object in our data array with the same exact x, y, width, and height dimensions. Let's fix this. First, let's fix the positioning along the x-axis. Instead of hard-coding 0 for this position, let's base it off of our data by updating to the following code. Function d(i) return I times width divided by data.length. We learned earlier that the first parameter passed to similar functions is the current data point. The second parameter is the index of this data point. We use this knowledge to evenly space our bars based on the width of our SVG canvas and the number of data points. Let's also set our padding, the space between bars. First, let's choose a padding, say 5 pixels, and add this below where we declare the SVG width, height, and overall padding. Now let's use this variable within our width function. Saving this file and refreshing our browser produces progress. We now have 7 separate bars, all evenly spaced. Time to set their height based on our data. Our height attribute is what needs to be updated next. Rather than hard-coding the height of each bar to 200 pixels, let's base this height on each data point's sales number, like so. .adder height function d return d.sales. Saving this file and refreshing our browser produces an upside-down bar graph. This makes sense once we understand how the XY coordinate system works with SVG. The origin, or 0, 0 coordinate, is always in the top left. So our bars currently grow down from the top. Let's make an adjustment based on this newfound knowledge. Instead of starting at 0, we need our height to start at a position of height minus our data point. So let's update our y attribute like so. Saving this file and refreshing our browser once again produces a right side up bar graph matching our data set. The third day with our lowest sales and the 6th day with our highest look right. Time to add some custom style to our bar graph. Let's color our bars. Eventually, our lowest sales day will be represented by a red bar, our highest by a green bar, and the rest will be light blue. For now, let's just set every bar to this light blue color. In order to do this, we need to set the fill attribute, which determines the color an SVG element is filled with. Add the following line to our existing code. This will set each bar to a light blue color. Save and refresh the browser to see our improved styling. As we've seen previously, hard-coding attribute values is rarely ever the best solution. Let's base our bar colors off of our dataset. To do so, we will make use of 2 D3 functions we have yet to see, D3.min and D3.max. Update the fill code to the following. This code uses the min and max functions to determine the minimum sales and maximum sales. We then use these min and max variables to set the bar color accordingly. Saving this file and refreshing the browser reveals our newly styled bar graph with colors based on data. Let's add some basic animation and interactivity next. Instead of starting all of our bars at their final fill color, let's start them all as the same light blue color and transition the min and max bars to their respective red and green shades. To do so, we will make use of another D3 function, transition. There are many settings for transitions, but we will focus on just two, duration and ease. Duration sets the length of time that the transition occurs over in milliseconds. Ease accepts an easing function. Easing functions control apparent motion in animations and make them appear smoother. In our case, we will use a simple easing function, d3.easeLinear. Here's the code we will be adding just above our existing fill code. We start with a light blue color and ease our way to the final color linearly over 2 seconds. Let's also add some very basic interactivity. Add the following code just below where we append the rect element near the top of our D3 code. This code simply says that upon a user clicking a bar, that day's best-selling beverage is alerted to the user. Saving and refreshing our browser, we can now see our transition from the light blue color to the min and max final colors of red and green. Also, if you click on a bar, you will be alerted with the best seller for that day. Lemonade on the highest sales day, water on the lowest sales day. We accomplished much in this video, including creating a bar graph, styling it, and adding animated transitions and interactivity. You may have noticed that the height of our bars in pixels is based on their sales values. What if, in a future project, we had sales in the thousands or even millions? This approach surely would not work. This is true, and is the subject we will tackle in the next video, adding a scale. Welcome to the third video of Harnessing the Power of D3, where we will be adding a scale to our bar graph. In this video, we will update our salesdata.json file to illustrate the need for a scale. We will then discuss several different types of D3 scales. Finally, we will discuss the role of domain and range in a D3 scale and choose a scale to apply to our bar graph. Currently, our bars fit nicely on the screen thanks to the fact that none of the sales values are greater than the height of our SVG canvas at 300 pixels. Our sales values currently map 1-to-1 to the pixels on our screen. We can test this by setting any day's sales property in salesdata.json to a number greater than 300. The bar will stop at the top of our SVG canvas visually, but if we inspect the bar, it actually extends off screen. We need a way to map our dataset's values to pixels on the screen so that the bars render properly. The actual height of this bar highlighted is over 27,000 pixels currently. Thankfully, we can use the D3 scale function to fix this. We will take a look at three of the more commonly used scales now. First up is the linear scale, which maps an input domain to an output range. The domain is typically the min and max value of your dataset, and the range is usually 0 to the max number of pixels we are working with. The width or height of our SVG canvas, for example. In this example, we are setting our domain from 4 to 105 and our range from 0 to 100. This scale would result in an output of 0.99 for an input of 5, and an output of 95.05 for an input of 100. Next, we will introduce the quantized scale. This scale breaks values up into buckets. Each bucket of values results in an output defined in the range. For example, here, any input below 0.5 will result in an output of red, and any input from 0.5 to 1 will result in an output of green. Finally, let's briefly touch on the ordinal scale. This scale directly maps specific inputs to outputs. In this example, an input of the string grass will always return the color green, and an input of sky will always return the color blue. Let's pretend that our lemonade stand grew into a large beverage distribution business. Our daily sales are now multiples of our lemonade stand. Replace the array in salesdata.json with this new array. Note all that is changed are the sales values. The values are now 1,000 times what they originally were. We clearly need a scale for our visualization now, as all of our values are well beyond the pixel height of our SVG canvas. The linear scale makes the most sense in this situation. Let's set one up based on our data. Add the following code to the top of our D3.json callback function. These lines of code use the D3 scale linear function with a domain from 0 to the max sales value in our dataset. The range stretches from 0 to the height of our SVG canvas. Now that our scale is set up, we need to apply it in two places below. First, change the y attribute to return height minus y scale of d.sales, and change the height attribute to return y scale of d.sales. Now that our height and y position are based on our newly scaled value, let's check out our graph. Everything looks just as it did before, but now our graph can dynamically scale any sales value input, be they a few dollars or several billion dollars. Next, we will finish building our bar graph by adding axes and labels. Welcome to the final video of Harnessing the Power of D3, where we will be adding axes and labels to our bar graph. We will begin by applying the scale we just created to our y-axis. We will then position and format both our y-axis and x-axis. Finally, we will add some simple labels to our bars to show their exact sales. D3 has several functions for placing axes on a visualization. We would like to position our y-axis to the left of our bar graph, so we add the following code. Var y-axis equals d3.axisLeft yscale.ticks5. This applies our y-scale to an axis with approximately 5 tick marks, which will appear to the left of the axis. We then add these lines to add this axis to our page within a G or group element. Now that the y-axis is set, let's add an x-axis which displays each day of the week from our data. First, add these lines to set up our x scale. This simply returns each day from our dataset and maps it evenly across the width of our SVG canvas. To apply this scale to an x-axis and display this axis, add var x-axis equals d3.axisBottom of x scale, and also append the group element. All axes begin at the origin, so the transform attribute simply moves our x-axis to the bottom of the bar graph. When we save this file and refresh our browser, we see a nice set of axes on our bar graph. Let's add one more touch to our bar graph before we wrap things up. Finally, we will add a label to each bar to show the exact sales figure. Add the following code to the bottom of the D3.json callback function, and we will walk through each piece. This block of code begins by selecting all text with the class label. It attaches our data from our D3.json callback and appends a text element with a class of label for each object within our data array. The text is set to each object's sales amount. We then set the text anchor attribute to middle and position our text further by relying on our width and height variables as well as our data array. Finally, we set some font styling. The sales totals are now displayed as labels at the top of each bar. In this section, we imported JSON data, built and styled a bar graph, and added axes and labels. In the next section, we will learn to work with GeoJSON data as we build a choropleth map. Welcome to the section of Harnessing the Power of D3, where we will be building a choropleth map with D3 using topo.json data. First, we will briefly discuss D3 mapping. Next, we will gain an understanding of both GeoJSON and topo.json data. We will then learn how to use command line tools to produce topo.json files. Finally, we will use D3 to style a choropleth map based on topo.json data. In this first video, we will build a foundational understanding of D3 maps and the data that powers them. We will begin by learning about the basics of D3 mapping. We will then discuss GeoJSON and topo.json data. Finally, we will learn where to find quality geographic data on the web. If you've yet to visit the D3 gallery on GitHub, I recommend checking it out. Some of the most interesting examples in this gallery are maps. D3 has powerful mapping capabilities. To get the most out of D3's features, one needs to understand their data, how to work with geographic data, such as GeoJSON and topo.json, and how to properly present this information in the form of a map. The first type of data we need to understand is GeoJSON. GeoJSON is a data format for encoding geographic information. The file extension for GeoJSON is simply .json. At its most basic level, GeoJSON files are simply JSON. GeoJSON can be used to represent geographic features such as points, lines, polygons, as well as more complex features such as multi-points and multi-polygons. GeoJSON.io is a great, simple resource for gaining an understanding of GeoJSON data structures. You can create different structures such as points, lines, and polygons on the map. The data structure on the right updates in real time. This is a great tool to begin understanding how GeoJSON encodes geographic features. One drawback of GeoJSON is that files can get rather large, tens to hundreds of megabytes. We're in luck though, as there is another option, topo.json. Topo.json is an extension of GeoJSON, which encodes topology. Converting a GeoJSON file to topo.json often results in an 80+% reduction in file size. This great size reduction is made possible by the fact that topo.json files reference shared line segments rather than duplicating the data for these shared lines. Think state borders, for example. GeoJSON would have two representations for the same border between Massachusetts and Connecticut, for example. A topo.json file, on the other hand, would only represent it once. This difference adds up, especially when one gets down to even finer levels of detail, such as individual counties. I highly recommend checking out the topo.json wiki on GitHub to learn more. So now that we have a basic understanding of GeoJSON, and topo.json data, the first question may naturally be, where do I find GeoJSON and topo.json data files to build maps with? The short answer, you don't. Typically, you will find something called a shapefile for the geographic region and detail level you are interested in. You will need to convert this shapefile to a GeoJSON file, then convert this GeoJSON to topo.json. This may sound like a lot of work, but there are some awesome command line tools available to make this process very accessible. We will work with these tools in the next video. As far as where to find geographic data, government websites for the respective geographic region are great resources. For example, in the US, I highly recommend looking through the data available on census.gov. In the next video, we will learn how to work with GeoJSON, topo.json, and their associated command line tools. Now that we understand what GeoJSON and topo.json are and their benefits to building maps with D3, let's work with them in our own project. First, we will find the necessary shapefile for our map. Next, we will find a suitable dataset to visualize on our map. We will then convert our shapefile into a GeoJSON file. Once we have a GeoJSON file, we will combine it with our dataset and produce a final topo.json file. Let's get started. First, let's set up a new project folder through the command mkdir d3 map, the name for our new project folder. And then navigate into this folder with cd d3 map. Now let's add a data folder through mkdir data. We should now have a D3 map project folder with a data subfolder. As far as our data set for this project, I have grabbed population density data from census.gov and exported it as a CSV. This CSV file is included in the course materials and should be placed in your project's data folder. We will take advantage of the resources on census.gov to grab our necessary shapefile. More specifically, under Geography, Maps and Data, Cartographic Boundary Files, we will choose County. We now have a choice of 3 different resolutions. We will choose the middle option so that we have solid resolution, but not any more than we need, as we will not be zooming in on this map. Download the 5m.zip folder. Now simply unzip this folder and place all of the contents within the data folder of our application. We now have the necessary shapefiles for our project. Next up, converting these shapefiles into a GeoJSON file. A quick aside, if you have trouble installing any of the following command line tools, including Homebrew, GDAL, and topo.json, do not worry. I have included the product of using these tools, final.json, in the course materials for video 3. With that said, I highly recommend installing and becoming familiar with these command line tools, as they are incredibly helpful for loading, cleaning up, and merging geographic data files. First, install Homebrew. Visit brew.sh to learn how. Homebrew makes it easy to install libraries and packages. Once Homebrew is installed, run brew install GDAL to use Homebrew to install the geospatial data abstraction library. We will use this library to convert shapefiles into GeoJSON files through the included binary OGR to OGR. Visit gdal.org to learn more about this library, and be sure to click through to the OGR to OGR specific section to gain an understanding of how this tool works and the many different options you have when working with shapefiles. I have previously installed GDAL, so we'll now move forward to using its included OGR to OGR binary. Navigate to the data folder of our D3 map application and run the following command. Again, make sure you are in the data folder and that all of your shapefiles are present. This command converts the CB 2015 US County 5M shapefile into a GeoJSON file called counties.json. This operation excludes data for all non-state US territories such as Guam, Puerto Rico, and the US Virgin Islands through the where clause. A little research online reveals the state FP entries above as being associated with non-state US territories. We name the output file counties.json. Note, you'll need to get used to researching geographic data and familiarizing yourself with the different options for filtering data that tools like OGR to OGR give you, as your shapefiles will very rarely match up to exactly what you need for your specific use case. Next up, we need to install the topo.json command line tool. We will install this tool using npm. If you do not yet have both Node and npm installed, please refer to the installation and setup section of this course and install them before proceeding. To install topo.json using npm, simply run the following on the command line: npm install -g topo.json. This installs the topo.json command line tool globally. I recommend looking through the topo.json command line reference on GitHub to familiarize yourself with the different options this tool provides you for converting and merging geographic data files. Again, I have previously installed this tool, so we will now move on to using it to merge our GeoJSON file with our CSV data file to produce a final topo.json file. Run the following command. This command merges the counties.json GeoJSON file with our population.csv data file. The ID property is the field common to both files on which these two files will be merged. The plus sign coerces GeoID to a number, as it is originally a string in the topo.json file, and without coercion would not match the number in the CSV. -p county, density declares that we want only the county and density fields returned as properties in our output file. -o final.json simply names the output file which results from this merge. Note the awesome reduction in file size. Typically, converting GeoJSON to topo.json can reduce file size by 80 to 90%. This is due to the elimination of redundancy that we discussed in the previous video. Let's take a look at our topo.json file. As you can see, we now have an array of geometries, which include the county and density properties we had declared earlier, as well as arc data to plot counties on our map. Now that we have final.json, we no longer need all of the pieces we used to put it together. We can delete all of our shapefiles, as well as counties.json and population.csv. Now that we have final.json, our topo.json file, which includes population density data, we can begin using D3 to build our map in the final video of this section. We now have a topo.json file which includes population density data by county for the United States. In this video, we will use D3 to translate this data into a choropleth map. First, we will learn how to load topo.json data and reference the features we are interested in. Next, we will set up the dimensions of our SVG canvas based on the current screen size. We will then properly position our map within this canvas using D3 projections. Finally, we will use a D3 library, D3 Scale Chromatic, to color US counties based on population density. Let's get started. Before we load our topo.json data and begin writing some D3 code, we need to set up a basic index.html file. The following file, which is available in the course resources, sets up a page titled D3 choropleth map with references to several libraries, a style sheet, and one local JavaScript file. The first external reference we have seen before, and it simply points to D3 v4. The second reference is new and points to the D3 topo.json library, which we will make use of shortly to work with our topo.json data. The final external reference points to the D3 scale chromatic library. This library provides sequential, diverging, and categorical color schemes, which are extremely helpful for coloring choropleth maps. Here is an example of what D3 scale chromatic will help us produce. This process was much more manual in past versions of D3. D3 scale chromatic is another benefit of working with the latest D3 libraries. This library is based on ColorBrewer, which you can try out at colorbrewer2.org, and is available thanks to Cynthia Brewer and her colleagues at the Penn State University Geography Department. The one local JavaScript file we reference here is choropleth.js, which is where we will be writing all of our D3 code. Let's create that file now. A quick note. To run any of the code in this section in the browser, simply set up a server like we did in the previous section through Python with python-m simple HTTP server. Typically, it'll serve your website at localhost 8000 in the browser. Let's load our topo.json data now. We use the same D3.json function we learned about in section 1, as topo.json in reality is simply a JSON file with added features. We then catch any errors by checking for them and logging them to the console if they appear. Note that the first parameter passed to the D3.json function is an error object. The second parameter is our data, which we will log so we can ensure we are loading the data we expect. Sure enough, we see the expected topology object with an array of counties that include county and density properties. Things are looking great, and we are ready to work with our data. As I'm sure you noticed, there's a lot going on in that topology object. There's an arcs array, a transform object, and our counties objects with useful data that is heavily nested. Thankfully, we can now take advantage of the D3 topo.json library we referenced in index.html to make our data easier to work with. The topo.json feature method returns the feature collection of the specified object within the given topology. In our case, data is our topology, the large object we just looked at, and data.objects.counties is the feature collection. We want the features of this collection, so we finish this line with .features. We now find that our data is much easier to work with, as we have an array of objects, each representing a US county, and each with an ID, geometry object, and properties object. I recommend checking out the documentation for the D3 topo.json client API here. We used the topo.json command line tool earlier to merge files and produce topo.json. This client API has several helpful functions for working with topo.json data client-side. Before setting up our map, we will take some time to size our SVG canvas based on current screen size. In section 1, we simply hard-coded the size of our canvas, but we can do better than that. Add the following code to choropleth.js. This code simply uses the browser window and document elements to determine the current screen size. Then the SVG code uses the determined width and height to set the width and height of our SVG canvas. Inspecting our page in the browser now reveals an SVG element which covers the entire browser window. Note that this canvas is not responsive, meaning if we resize the window, the canvas will not resize dynamically. Don't worry though, we will learn how to make our canvas responsive in the final section of this volume. It's finally time to add our map to the SVG canvas. The world is not flat, yet our screens are. So first we need to choose a projection for our map. A projection will do a solid job of projecting a sphere onto a plane. If you'd like to learn more about the projection details, I encourage you to read through the D3.Geo documentation here. There are many projections to choose from, depending on your needs. For our case, the GeoAlbers USA projection will work perfectly. This is a US-centric projection, which reduces the size of Alaska to just over 1/3 of its true relative area. First, we set our projection to D3.GeoAlbers USA. We then pass this projection to a path generator, D3.GeoPath. This path can now be used to generate an SVG path for each element of our county's feature collection with the following code. This final block of code should look familiar. We are selecting all elements with class county, of which there are none at first. We then attach entering data to this selection through the enter function. We then pass the path we set above in and add the county class to each one. Let's add some basic county styles now. Our style sheet is very basic and simply sets the stroke to gray and stroke width to 0.3 pixels for our county pass. Let's take a look at the result in our browser. We now have a map of all US counties, including Alaska and Hawaii counties. Now the exciting part. Let's use our population density data to color this map. First, let's simply hard code the county colors so we get the hang of the basics. The fill attribute is what we are concerned with here. So let's set our fill color based on data in a very basic way. Let's say if the population density is greater than 200, the color will be red, otherwise green. To do so, we need to access our data as we have previously and base the color off the density property. Progress. Our county coloring is now based off of our data, but we can do much better. Let's now revisit our old friend, the D3 scale, in order to put some final polish on our map. Let's start off by determining the max population density using the convenient D3.max function. We can then use this value within a linear scale to scale our densities down to a 0 to 1 range. We will now take advantage of the D3 scale chromatic library we referenced earlier in our index.html. There are many color interpolations to choose from, but let's go with reds. So the higher the population density, the darker red a county will appear. We are going to use a sequential scale with interpolate reds passed in. Now let's use this to interpolate our scaled density data. You'll notice a couple things with this result. One, the vast majority of our map is light colored. This is due to the fact that there are relatively few extremely dense counties, as you notice around Los Angeles and New York, for example. We can improve the visualization by setting the upper end of our scales domain to something other than the max, say the mean. You may also notice a couple counties which appear black, namely in South Dakota as well as Alaska. This is a result of there being no density data available for these counties. We will clean up this visually by defaulting their density to 0. Here are the changes we're making. We'll update the D3.max function to D3.mean instead. We will also use a ternary statement to default density to 0 in cases of missing data. Much better. We now produced a choropleth map which clearly shows relative population density by county across the United States. We learned and accomplished much in this section. We started off by briefly learning about the GeoJSON and TopoJSON data formats. We then worked with command line tools in order to convert shapefiles into a GeoJSON file, and combine GeoJSON with CSV to produce a TopoJSON file. Finally, we used D3 to build a choropleth map based on our data. In the next section, we will be building off all of the skills we have learned in the first two sections and building an interactive dashboard with multiple visualizations. Welcome to the section of Harnessing the Power of D3, where we will add some finishing touches to our choropleth map, including interactivity. First, we will add a legend to our map. Next, we will add some basic interactivity in the form of zooming. Finally, we will learn how to add custom tooltips to our map. Let's get started. In this first video, we will add a legend to our choropleth map. We will begin by using a D3 scale to map our map colors to population density values. We will then add labels as well as a title to our legend. Finally, we will learn how to use flexible settings to size and position our legend. Let's first revisit the product of last section's work. We have a nice choropleth map of population density by county. We can clearly see urban areas with high densities and the plain states with much lower densities. However, we currently have no idea what range of values these colors actually equate to. By the end of this video, we will. We are going to start off by creating a settings object for the container which will hold our legend container. You could simply hard code these values into the appropriate attributes of our legend container, but our approach will allow for much more flexibility. These settings are not only used to size and position this container, but are also relied on by the text and color boxes which will appear in our scale. Our container will be an SVG rectangle, so it requires X, Y, width, and height attributes. The Rx and Ry attributes are optional, and we use them to slightly round the corners of our container. The final attribute we set is ID. We have several styles for this container that will not change, so we set them in CSS rather than here. Here are our basic legend container styles: a white background with 0.9 opacity, and a thin gray border set through stroke and stroke width. Back to choropleth.js. I'd like you to notice how many times we are calling .adder to set attributes. There is actually a cleaner way to do this, but it is not built into the core D3 v4 library. That's fine though, because D3 is modular and allows us to easily import extensions. Let's do so now. The D3 selection multi-module has exactly what we're looking for. A quick glance through the documentation reveals that this module will allow us to use the plural form of both adder and style, adders and styles, to set multiple attributes or styles concisely. All we need to do to gain access to this functionality is add the following script tag to our index.html. Simply add this script tag and we will be ready to refactor our code. Here we see our refactored code looking much cleaner. Note how we simply use the appropriate properties from our settings object here. This means that this code will never need to change. If we would like to change the size or position of our container, we simply need to update the settings object. Let's take a look at what our map looks like now. We now see our simple legend container below our map. Let's begin adding some content to this container. We will now create color boxes for each color that appears within our map, which we will soon label to give viewers an idea of what population density range maps to each color. In preparation, we're going to make an adjustment to our color scale. We'll now be using a quantized scale rather than linear. This scale will be broken up into 6 blocks ranging from 0 to the mean of our data. Now back to our legend. Let's make each box 50 pixels wide and 15 pixels tall, with a Y value dependent upon our container settings Y value. You can now see how settings objects like this can help make our visualizations more flexible. We next set our legend data equal to the color scale range we just updated. We'll now append a G element with the class legend to our visualization for each member of the legend data array. Now it's time to set the attributes and styles of each of our legend color rectangles. We know that X, Y, width, and height attributes are necessary, and all but the X attribute comes from our legend box settings object. Our X attribute depends on legend box settings, along with the index of each value in our legend data array. This way our colored boxes are laid out one after another and will resemble a scale. We now use the plural styles property to fill each of our boxes with the appropriate color. Let's take a look at the result in our browser. We have successfully added a color scale to our legend. Now it's time to label this scale. Before we get started appending labels to the legend, we should write a couple functions to format our data as well as get our domain density values from our range. First, let's make use of D3 formatting for the first time. We would like to format our values to 1 decimal place, which we can accomplish with D3 like so. I encourage you to take a look at the D3 format documentation on GitHub to learn more about the many options available. We will now make use of the invert extent function to go backwards and retrieve domain values from our range. This function will return an array to us with the lower and upper bound for each color within our legend. We will now make use of this function to produce legend labels. We once again make use of our settings object in order to properly place our labels. Let's take a look at the result. Finally, we can equate colors on our map to actual population density ranges. We've left some room at the top of our legend container to title our map. Let's do so now. We again make use of adders and styles, as well as our settings objects, to position our title. A note here, the hard-coded values here, such as 13 and 29, were simply determined through trial and error. You'll find yourself doing a bit of bouncing back and forth between code editor and browser to position, size, and style things to your liking. We now have a choropleth map with a title and legend. Nice work! In the next video, we will be adding zoom functionality to our map. We now have a choropleth map with an informative legend. In this video, we will use D3 to add zooming functionality to our map. First, we will add a click handler to our code, which will cause our map to zoom in and out appropriately. Next, we will learn more about translations, which we use to perform zooming. Finally, we will briefly take a look at the D3 Zoom module and its many options. Let's get started. We will start off by making one very small update to our code in preparation for zooming. Add a new attribute on our county G element, cursor pointer. This change simply updates our cursor whenever we hover over a county on our map. Let's take a look in our browser. Now we can clearly tell that each of these counties are clickable, and we should expect some form of interactivity when clicking, in our case, zooming. Let's set up our zoom click handler now. Let's continue to follow the pattern of creating a settings object. Our zoom settings will be pretty basic. We want to set a zoom duration in milliseconds, which is simply how long our zoom will take. The larger the number, the slower the zoom. Let's initialize this to 1000 milliseconds, or 1 second. We will also set up an easing function, is a method of distorting time to control apparent motion in an animation. we will choose D3.ease cubic out, which starts out relatively quick, then slows down towards the end of the animation. We should also set a zoom level. The higher the number, the closer we will zoom in on the clicked county. We'll initialize this to 5. Now it's time to set up our click handler. Each time a user clicks anywhere on our map, this function will be triggered. We begin by declaring some variables we'll be using within this function, namely x and y coordinates, as well as the zoom level. Now comes the interesting portion of our click handler. First, we check to see if the user clicked on an element with data, one of the counties, and whether that county is already centered. If the user indeed clicked on a county which is not currently centered, we grab the centroid of that GeoJSON object by use of D3's path.centroid function. We set our x-coordinate to the x-coordinate of this centroid, which is the 0 index of centroid. Likewise, we grab the y-coordinate from index 1. We then set our zoom level to the value from our settings object, and the centered property is set to our current county, D. On the other hand, if the user clicked outside of the map, or clicked on a county which they were already zoomed and centered on, then the x and y coordinates, zoom level, and centered properties would be set back to their defaults. Now that we have our variables properly set, we will use a D3 transition along with a translation to properly zoom in or out. A transition is an animated change to the DOM. You can learn more about them on the D3 transitions page on GitHub. Our transition will make use of the duration and ease we set earlier in our settings object. The final line of our click handler makes use of transform in order to translate our view to the current state specified by the x and y coordinates as well as the zoom level. Now we need to attach our click handler to our visualization. First, let's append a background rectangle to the SVG and attach our click handler through onClickClicked. This background will act to zoom out our map when someone clicks outside of any of the counties. Finally, we'll need to add this clicked click handler to each of our counties. To do so, simply attach it to the end of where we append our G county element for each county within our data with onClickClicked once again. Let's take a look at the results in our browser. We now have zooming functionality on our map. Click a county to zoom in and center the map. Click on the same county or outside the map to zoom back out. Let's tweak our settings to see the effect they have on our zoom. Here, we've increased our zoom level from 5 to 20, and you can see the result. Here, we've tripled the zoom duration to 3000 milliseconds, and you can see how much slower zooming in and out is. Here, we've updated the easing function to D3.easeBounceIn. And you can see the dramatic effect. Obviously, this is not the desired easing for a map, but there are cases where this easing could work well for a visualization. I encourage you to check out other easing options on the D3Ease GitHub page and play around with them to see their effects. We made use of some basic zooming functionality with transitions, translations, and transforms in this video. I encourage you to check out the D3 Zoom documentation on GitHub to see many more options in version 4 of D3. I also encourage you to play around with these options to see what may work best for your personal projects. In the final video of this section, we will be adding custom tooltips to our map. In this final video of making D3 visualizations interactive, we will be adding custom tooltips to our map. First, we will add a basic tooltip through use of the title attribute. Next, we will create an improved tooltip through user events. Finally, we will use CSS to customize our tooltip. Let's get started. We will begin by adding the most basic tooltip possible. SVG elements have a title property, which can be used to show a tooltip. We simply append a title to each of our counties, and then use our data to set title to each county name. We see a fairly underwhelming result. The tooltip is small, unstyled, and rather slow to load and unload. Clearly we can do better, so let's get to it. First, let's create a tooltip variable and attach it to a div. We will assign this div a class of tooltip, which we will style with CSS shortly. We initialize this div's opacity to 0, as we want it hidden until a county is hovered over. Next, just as we added a click handler earlier, we now want to add handlers for mousing over a county, as well as mousing out of a county. On mouse over, we will make use of D3 transitions once again. Let's set a short duration so our tooltips load very quickly. We will, of course, update our opacity so that the tooltip is now visible. We set the HTML to the county and density so that our tooltips are informative. Finally, we take advantage of the D3.event property to position our tooltips according to current cursor position. We also need to handle mouse out events. Otherwise, our map would quickly become cluttered with dozens and eventually hundreds of tooltips as we hover over the map. We simply transition the opacity back to 0 over the course of 300 milliseconds. Now let's set some styles for our tooltip class. These are the simple styles we've chosen, but feel free to alter them to see the results. Let's try out our new tooltips in the browser. We now have custom tooltips which are informative and much faster, also better designed than the basic title tooltips we saw earlier. We accomplished much in this section, including adding a legend, making our map zoomable, and adding custom tooltips. We learned how to work with D3 modules such as D3 Selection Multi in order to make setting attributes and styles more concise. We learned about the flexibility afforded by creating settings objects for pieces of our visualization. We learned about detecting and reacting to user events such as click, mouse over, and mouse out. We learned about D3 transitions and easing functions, as well as D3.format for formatting numeric values. In the next section, we will be switching gears and going through an overview of Angular 2. Welcome to the section of Introduction to Angular 2, Angular 2 Overview, where we will discuss Angular 2 fundamentals. We will begin by discussing modularity in Angular 2 apps. Next, we will tackle components and their importance within Angular 2 apps. After this, we will discuss data and event binding. We will then go over services in Angular 2. Finally, we will wrap up this section by discussing unit testing in Angular 2 applications. In this first video, we will learn about modularity in Angular 2 applications. First, we will take a look at ng module and root module, which every Angular 2 application needs. Next, we will discuss both JavaScript modules and Angular modules. We will wrap this video up by discussing some benefits of modular design. Let's open up D3 Angular 2 app, which we built in the installation and setup portion of this course earlier. Let's take a look at app.module.ts. This file is the root module of our application. Every Angular 2 application needs a root module, and by convention, this root module is named app module. Although you can name it whatever you like, sticking to convention makes sense here. The root module makes use of ng module and its metadata to more or less define the module. We import any necessary dependencies, such as browser module, which is required by any application that will run in the browser. These imports are declared in the imports array. Browser module includes core directives like ngIf and ngFor. We declare components, directives, and pipes which belong to this module in the declarations array. So far, all we have to declare is app component. An important note here, each component, directive, and pipe should only belong to one module. So in our example, app component belongs to our root module and should not be included in any other module's declarations array. We declare any services that are part of this module in the providers array, of which we currently have none. Finally, we define which component will be used to bootstrap our application in the bootstrap array. Speaking of bootstrapping, let's jump over to main.ts to quickly review how that is done. In main.ts, we bootstrap our root component by passing it to platform browser dynamic.bootstrap module. Since we already declared app component in the bootstrap array of our root module, whenever app component selector is encountered in the DOM, in our case, the element D3.app, our application will be bootstrapped. You may not be aware, but you have already been working with JavaScript modules. JavaScript modules allow us to share our code across our application. We can do so by making use of import and export statements. For example, you see here that we are importing app module from app.module. This is made possible by a statement we used in app.module.ts. Here you can see we explicitly export the app module class so that we can import it elsewhere in our application, as we just saw it in main.ts. You can only import modules which have already been exported. We also see a great example of an Angular module here. Any module declared with ng module metadata is an Angular module. This modular approach allows us to easily break our applications up into logical pieces, group shared functionality, components, directives, and pipes, and to easily share these modules with different parts of our app. Now that we have an understanding of modules, let's discuss components, which are extremely important building blocks in any Angular 2 application. We now understand the details behind and benefits of modules in Angular 2 applications. Now let's take a look at components and the important roles they play in Angular 2 apps. We will break our discussion of components down into three sections. First, we will take a look at import statements and their role in components. Next, we will discuss the component decorator and the metadata associated with components. This will include properties such as selector, template and template URL, styles and style URLs, and providers. Finally, we will dive into the component class. Let's get started. We use import statements to gain access to functionality we need within our component. Every Angular 2 component will need to import component from Angular core, as we use the @component decorator to define our component's metadata. Let's assume our component has changed and now accepts an input property. Say name, for example. We gain access to this property through the @import decorator, like so. Here we simply declare name as a string and decorate it with the input decorator. However, this will not work, at least not yet, because our component does not know anything about this decorator. This is easy to solve though, through simply adding input to our imports. Input is also located in Angular/core, so we can just add it here. A quick tip regarding knowledge of where different decorators, directives, pipes are located. Visit this site, angular.io/docs/ts/latest/API to see where to import different elements from, and also to learn more information about them. It's not just built-in Angular elements that we'll want to import. Often, you will be importing other components which you have created. Ignore the error here, as I just have not created this component yet. For example, let's say you need access to this child component once it is created. You would import it like so. Now you would have access. So you could put it in your HTML template and reference it like this through its selector. I favor putting a space between imports which come from outside my application, such as Angular core, and imports which I have created, such as child components. This just makes it easier to find specific imports as their number grows. Now let's discuss the all-important component metadata. While the logic behind our component will be located in the class, metadata tells Angular how to process this class, including what template to attach it to, how to style that template, what selector in the HTML is associated with this component, and more. First off, the selector. This simply specifies the CSS selector which identifies this component. So wherever this selector is encountered within the HTML, this component will be rendered. Note that the most common form of selector is an element, but attributes and classes are also allowed, as this is simply a CSS selector. Next up is the template associated with this component. You have two options here. The first is to use the template property and declare the template inline like so. Use backticks to declare a multi-line inline template. This approach, however, is far from ideal. Longer HTML templates can quickly bloat your component, and you also do not get the IntelliSense that an actual HTML file would provide you. The other option, and the one I recommend if your template is over a few lines long, is the template URL property. Here you simply declare the relative path to an external template and place your HTML in that template. As you see, we now have rich IntelliSense as well as auto-completion. Notice the other metadata property that we added, module ID. This is very important and is what allowed us to use a relative path rather than an absolute path to our template. As long as you place your HTML and CSS files within the same folder as the component referencing their location is as simple as this example. Just make sure to add this module ID property and set it to module.id. Now that we know how to set the template for our component, how do we style it? Well, in reality, you could simply have one overarching style sheet for your entire application, but I do not recommend that. Instead, take advantage of the ability to set styles specifically for your individual component. Similar to the template options, you can either do so inline like this with the styles property, or you can reference external style sheets with style URLs, which I personally prefer and recommend. Note the plural, style URLs, so you can indeed reference multiple style sheets. So now we have declared a CSS selector for our component, attached a template, and set some styles. But what if we need to call a service to get data for our component? Well, then we can use the providers array to list dependency injection providers for this component. An important note here, this will allow this component and its children to access the declared providers. In almost all cases, you will only want to declare each provider once and do so as high in the chain as possible. For example, if multiple child components will need access to a certain provider, declare it within the highest level component, and you will have access in those children. On the other hand, if only a single component needs access to a provider, just declare it in that component's providers array. This does not, however, mean that you can forget to import your service in child components. You will still need to remember to include this import in any component which makes use of this service. We have now learned about selector, template, and template URL, styles and style URLs, and the providers array. Those are the main metadata properties you will work with frequently. More properties and information about them can be found in the Angular 2 cheat sheet, which I highly recommend checking out at angular.io/docs/ts/latest/guide/cheat sheet. Finally, let's discuss the meat of a component, its class. This is where all the logic for our component resides. We declare variables here which can be bound to the template. We can set up a constructor function which instantiates values. You'll notice that we use this to refer to this component class. If you're coming to Angular 2 from an Angular 1 background, this is a significant change from $scope and falls more in line with the controller as syntax from Angular 1. We can take advantage of lifecycle hooks to gain visibility into key life moments of a component. ng on init, ng on changes, and ng on destroy are lifecycle hooks you will become familiar with early on when developing Angular 2 applications. A quick tip here. If you plan on calling services to get data when your component loads, you could handle this in the constructor, but I highly recommend doing so in the ng on init lifecycle hook instead. The main motivation behind this centers on testability. You will be able to intercept this lifecycle hook and, for example, return mock data to a test. You cannot do this with the constructor. Continuing on, we can also define methods in our class, which can be bound to user events. We will spend a good amount of time in component classes in the next section when we use what we are learning in this introduction to build actual Angular 2 components. In the next video, we will learn about data and event binding in Angular 2. Now that we understand components, let's take a look at how we bind data between our class and template in Angular 2. First, we will discuss simple interpolation. Next, we will learn about one-way data binding. We will then switch gears to discuss event binding. Finally, we will put all we've learned together as we go over two-way data binding. We have already seen the use of interpolation in our simple Angular 2 app. The double curly braces signify interpolation, and in our example, course resolves to the string Angular 2, as this is the string it is set to in our component class. The favorite color variable is more interesting though, as we will soon see. Interpolation is one-way data bound. One-way data binding flows either from the data source to the target, as you see with interpolation, or here with brackets. In these cases, the expression is set in the component class and interpolated in the template. This syntax modifies the style of the element. In these cases, background, as well as color. One-way data binding can also flow in the opposite direction, from the target to the source. This is often referred to as event binding, and you will notice an example here with our button's click handler. Click is a DOM event. So we are simply telling Angular that when this click event on button is fired, call the change background color method from our component class. As you can see in our component class, this method checks the current background color and alternates it between white and gray as the button is clicked. Two-way data binding is often referred to as a banana in a box due to the parentheses inside of brackets. If we glance back at the two forms of one-way data binding quickly, we will see why this syntax makes complete sense. Two-way data binding is a combination of both forms of one-way data binding. Any change to the data source will be reflected in the target, and any change to the target will be reflected in the source. You'll notice as we change the color, it is instantly reflected both in the text and in the style. Pretty cool, huh? Since this is directly updating the color property, we could even use hex values. That is a brief introduction to data and event binding in Angular 2. We will be digging in much deeper in the next section as we build a basic Angular 2 app. I have included this example in the course materials if you would like to play around with data binding some more on your own, which I recommend. Simply replace app.component.ts and app.module.ts with the updated files I've provided for this video. In the next video, we will discuss services in Angular 2. We will often be pulling in data from a server or other remote resource and pushing data back up as well. In order to do so efficiently, we will need to learn how to create and use services in Angular 2 applications. We will begin by discussing dependency injection and how to make use of it in order to inject services into components. We will also discuss the injectable decorator and its importance to services. We will then discuss the HTTP client and how to use it within an Angular service. HTTP.get calls return RxJS observables, which we will discuss in this chapter. Finally, we will discuss turning observables into promises in case working with promises is your preferred approach. We will be using something called the in-memory Web API module in this video. This is an optional service which is not part of Angular core, so we will need to import it in app.module.ts like so. This service comes from the Angular 2 in-memory Web API library, which is installed when we ran npm install during installation and setup. As you can see here, it was included as a dependency in package.json. We also need to include in-memory Web API module in the imports array for our app module. We configure our in-memory Web API module through for_root, which takes an in-memory data service that we will quickly set up now. Create a file called groceries-data.ts in the app directory and fill it with the following code. Here we are importing the in-memory DB service from Angular 2 in-memory Web API. We then need to create an in-memory DB service. We will call ours groceries data. We use the createDB method to seed data into our service. In our case, a simple list of grocery item names. We then return this array of groceries. The reason we created this service is so that we can mock an HTTP backend. Typically, you will be using HTTP to communicate with your server or third-party APIs. This is beyond the scope of this course, so we will be utilizing this in-memory Web API instead. All files which have been updated and added since the installation and setup architecture are included in the course materials. Let's briefly walk through the changes to app.module.ts, as well as introduce some important RxJS imports. You'll notice a couple additional imports in app.module.ts. First, there is Forms module. We will be making use of some basic features of Angular 2 Forms to allow users to add groceries to the list, so we need to import Forms module here. We will also be using the HTTP module to pull data into our app through HTTP calls, so we import that module as well. Of course, we remember to include these modules in the imports array. Unlike our very basic starter app, this app will have a child component, so we import groceries list component here and declare it in the declarations array. Continuing on, in app.component.js, we now reference our child component in the inline template. You'll also notice that we import RxJS operators. We could simply import the entire RxJS library. However, this library is very large, and we only need a few features of it. So instead, we will import those individual features into an RxJS operators file and simply reference that file here. Here's that file with just the 4 features we are interested in being imported. Let's create a subfolder, groceries, within our app directory, which holds all of our groceries list component logic, template, service, and type definitions. Let's walk through these files now. First, we will discuss grocery.ts, which is where we define the grocery class. This is about as simple as a class gets. Grocery is simply an object with one property, name, which is of type string. Although this is extremely simple, it will give us an opportunity to show how to use TypeScript typings in an app. Now let's take a look at groceries-list.component.ts. You'll notice that we import what we need, including on init, so we can take advantage of this lifecycle hook. We also import the grocery class, which we just created, as well as the grocery service, which we will be creating soon. This grocery service will need to be injected into the providers array, which provides access to this service to this component, as well as any child components, of which there are currently none. Next, we declare our component class and state that it implements on init. You see here we are using typings as we declare error message of type string and groceries as an array of grocery objects, the class we just created. Within our constructor, we instantiate a private instance of grocery service as underscore grocery service. The underscore is simply added to follow the convention of prepending private class members with an underscore. Now let's take advantage of the ng-oninit lifecycle hook. When this component loads, we want to see a list of groceries. So let's call this class's getGroceries method, which we will create now. We will use our grocery service and call its soon-to-be-created getGroceries method. This method will make an HTTP call and return an observable. You can think of an observable as a stream of events. We listen for events within this stream by subscribing to it. Depending upon the results of the call, we will either get back our groceries or we will get back an error. We handle both cases using arrow functions. This is simply a more concise way to write a function expression. So now we can see a list of groceries, but what if we want to add to this list? Well, we can create an addGrocery method for that functionality. Here we use typing again to state that we expect a name argument of type string. We check to make sure that the argument is passed in. Otherwise, we immediately return and nothing is added. If a name was passed, we call the addGrocery method of our grocery service. Again, the response will be an observable, which we will need to subscribe to, and then handle a successful response by pushing the new grocery to our existing array, or handling an error. It's time to step into our service class now. Let's walk through our imports briefly. We will be working with HTTP to make calls, so we import several modules from Angular/HTTP, namely headers, HTTP, request options, and response. We should also import the injectable decorator, which we will discuss more in just a second. As we've already discussed, we will be working with observables, so we import observable from rxjs/observable. Finally, we once again import our grocery class. I recommend including the @injectable decorator on every service you create. Technically, we did not need it here, as this class does not need any dependencies to be injected to it. However, for consistency's sake, it is recommended to always include this decorator. That way, when you encounter a situation where it is required, it is already present. Now let's fill in our grocery service class. First, we establish an API endpoint for our service to call. Remember, our in-memory web API module will step in at this point. We instantiate our private HTTP method in the constructor. Next, we will use it within both a getGroceries and addGrocery method. GetGroceries will expect an observable array of grocery objects to be returned. It will call http.get on the groceries URL. .map and .catch should look familiar, as we imported them earlier in our rxjs operators file. These are rxjs methods. Upon a successful HTTP response, we map over the response and call the extract data function, which we will define soon. Upon an error, we catch this error and handle it through a method that, again, we will define soon. addGrocery will expect an observable grocery object to be returned. We set the body, headers, and options like so. And then we call http.post with them, as well as the URL passed in. We handle the response just as we did above. Our response is actually in the form of a string. We need to parse this response to JSON and then grab its data property. This is what our extract data method does. In case of an error, we format and log an error message. We also return our error message as an observable through observable.throw. Our component and service are now in solid shape. Let's take a quick look at our HTML template before testing this in the browser. Our HTML template is very straightforward. First, we use ng4 to loop through each grocery item in the groceries array and print its name to the screen. If an error is encountered, it is printed to the screen. We use ngIf to control this. Finally, we make use of Angular 2 forms by using an input of new grocery name and passing this input's value into the addGrocery method. When the addGrocery button is clicked, this method is called. Let's check the results in our browser. As you can see, our groceries are listed as the page loads. And when we type a new name and click the Add Grocery button, the new item is added to our list. Pretty sweet. I highly recommend working with observables in Angular 2. They are very powerful, and we have barely scratched the surface with regards to them here. However, if you still prefer to work with promises, there are only a couple changes you'll need to make. First, within our service class, you'll now expect promises to be returned from getGroceries, as well as addGrocery, rather than observables. Also, you will need to use the toPromise method in both getGroceries and addGrocery. Promises do not have a map method, so this will need to be updated to .then. We will also need to update where we return observable.throw to return promise.reject within the handle error method. Now in our component, we only need to change .subscribe to .then, as promises do not have a subscribe method. These are all the changes we need to make. Let's check out our app in the browser. We are now working with promises rather than observables, but the app functions exactly the same. We accomplished much in this video. We learned how to add the in-memory web API module to our app. We added the HTTP module and built out a service using it. We worked with both observables and promises. Finally, we worked with Angular 2 forms and made use of ng-for as well as ng-if. In the next video, we will create basic unit tests for the app we just built. We should aim to build testable applications, and Angular 2 makes it easy to set up both unit tests and end-to-end tests. In this course, we will focus on unit testing using the Jasmine testing framework and the Karma test runner. We will begin by discussing the tools we will be using for testing our app. We will then walk through setting up a basic testing architecture. Finally, we will write one very basic test and run it to confirm that our testing setup works. Our testing framework of choice will be Jasmine. You will find that well-written test suites read like a sentence. You begin by using Jasmine's describe function, which takes a name for your test, and a function which includes your test suite. You will then have one or many it blocks, which include a string describing your test, along with a function that includes one or more expect statements in which you test your code. There is much more to the Jasmine framework, and I encourage you to read more about it at jasmine.github.io. We will be using version 2.5 in this course. Our test runner of choice will be Karma. Karma takes care of all the configuration necessary to get our tests up and running in a browser. You can learn more about Karma at karma-runner.github.io. Let's briefly go over our testing setup. There are 5 files you will need to be aware of to get your testing structure up and running. Each of these files is available in the course materials. This structure comes directly from the official Angular 2 documentation. First of all, we have made changes to 2 files that are already part of our app, package.json and systemjs.config.js. In package.json, you will notice that we have added some test-specific scripts, as you will see here with test as well as test once. Note how similar the start and test scripts are. Start here and test, which we just added. We've already used npm start several times. npm test transpiles our TypeScript and then watches our TypeScript files for any changes and recompiles. It then reruns our tests each time our TypeScript changes. We have also added Jasmine and Karma dev dependencies. In order to install these dependencies, you will need to open a terminal to your project's root directory and run npm install. We have grabbed our systemjs.config.js file directly from the Angular 2 docs to match up with the recommended setup. Now moving on to the 3 files we have added to our project. First is systemjs.config.extras.js. This is an optional file which you may need to eventually add app-specific settings to for things such as barrels, which is beyond the scope of this course. Just know that this file will most likely be necessary as your app grows in complexity. The next file is karma.conf.js, which sets all configurations for our Karma test runner. We set our base JavaScript and TypeScript directories, in our case, /app. We also set our testing framework to Jasmine. This is a large file with many settings, and I encourage you to head over to the Karma website to learn more about all the available options. The final file we've added is karma-test-shim.js, which simply prepares Karma specifically for the Angular 2 environment. It's now time to run a sample test. Create a file called test.spec.ts in the app directory and add the following code. Each of our test files needs a .spec.ts extension in order for the test to be run by Karma. This test simply expects true to equal true. All we are doing here is testing our setup. Save this file and run npm test in your terminal. You will see several lines printed at the terminal as the test runs, and you should see executed 1 of 1 success. That's it. We have successfully set up a testing structure and run our first test. In the next section, we will add much more interesting test specs to the application we build. We have learned much in this section, including understanding modularity in Angular 2 apps, understanding components, data and event binding details, using services in Angular 2, and setting up a testing structure. In the next section, we will use all we learned in this section to build a fully tested Angular 2 application. Welcome to the section of Introduction to Angular 2, Building an Angular 2 App. We will begin by introducing Angular CLI, which makes creating a basic Angular 2 app very easy. Next, we will work with structural directives and class bindings to make our template more dynamic. We will then review creating services as well as mock data. Next, we will introduce Angular 2 forms and add one to our app. We will then discuss adding routing to our app. Finally, we will wrap things up by writing some unit tests. In this first video, we will learn about the Angular 2 command line interface. First, we will discuss the benefits of Angular CLI, specifically in relation to our manual process in installation and setup. We will then walk through creating a new project with the Angular CLI. We'll wrap things up by taking a look at the default structure of an application created with the CLI. CLI stands for Command Line Interface, and the Angular CLI makes it easy to create Angular 2 apps with a default set of configurations already built in. Out of the box, you will have a build system, now Webpack instead of System.js, infrastructure for both unit tests and end-to-end tests, and much more. All this with only one command on the command line. To learn more about Angular CLI and its many options and capabilities, visit the project's GitHub page. Much of what the CLI does for you, we set up manually in the installation and setup portion of this course. I highly recommend checking those videos out if you haven't already. I also recommend creating a couple projects manually before diving into the CLI. A knowledge of build tools, typing configurations, testing infrastructure, and other setup details goes a long way in truly having a solid understanding of the Angular 2 landscape. With that said, we are now going to install and run Angular CLI to create the project we will be working on throughout this section. To install Angular CLI, we are going to make use of, you guessed it, npm. Run npm install-g Angular CLI to install Angular CLI globally. I have already installed CLI previously, so feel free to pause the video now as your installation finishes up. Now for the fun part. To create a new Angular 2 app, simply run ng-new and then the name of your application. We're going to build a recipes app in this section, so let's run ng-new recipes. This process can take a bit of time, so we will now jump ahead. That's it. Our app has been created. Let's jump into it with cd recipes. Now to run our app, we use another Angular CLI command, ng-serve. We see here that our app is running on localhost 4200. Navigating to localhost:4200 in the browser reveals that our app is indeed up and running. Let's now take a look at the structure of the Angular 2 app, which we just created through the CLI. Open up our newly created project in your IDE of choice. We're going to walk through the app structure. You'll notice 3 folders. E2E, which contains configuration for end-to-end testing. We will not be diving into this in this course. Node modules, which we have seen before, and contains our project dependencies such as necessary Angular libraries. And source, which contains all of our Angular 2 code, and which we'll take a much closer look at shortly. Below these folders, you'll notice several configuration files. We will be focusing on package.json as well as the README. Take a look at the package.json file first. This should begin to look familiar at this point, as we have looked at similar package.json files in the past. The scripts object reveals the defined commands such as ngserve to start our app and ngtest to run unit tests. You'll find the usual suspects for an Angular 2 app in the dependencies and dev dependencies, including Angular core libraries, Jasmine and Karma libraries for testing, as well as a TypeScript file. Now let's hop over to the README. The README provides us with some useful info and some important links to further details. We see commands for running our app in a development environment, building for production, and running both unit and end-to-end tests. We also notice a reference to scaffolding. We will be using scaffolding in this section to create services and components. Now let's take a look inside the source folder. You'll notice several familiar files such as tsconfig.json, a global styles file which we will not use as we will add styles to our individual components. You'll also find a very basic index.html here, as well as main.ts. Main.ts bootstraps our app, as we've done before. However, in this case, we first check to see if we should run the app in production mode. Our environment variables, which this if block uses, reside in the environments folder. The assets folder is where we would place any static assets such as image files. Finally, all of our Angular 2 code will live in the app folder. Currently, you'll find app.module.ts and a very simple app component here, which is what was loaded when we ran this app in the browser. Now that we have an Angular 2 app up and running and have familiarized ourselves with the app structure, let's add to our app component and make it more dynamic. We have an Angular 2 app up and running through use of Angular CLI. Let's now customize the app component which has already been created for us. We will begin by setting up a basic recipe object in our component class and using interpolation to display it in our template. We will then make use of structural directives, namely ng4, to add elements to our DOM from an array of recipes. Finally, we will use class bindings to style the DOM based on a property of our recipe objects. Let's get started. Let's change the title in app.component.ts to recipes, and also declare that title is of type string. When the app updates in the browser, we notice that the title is now changed to recipes. Let's add an unordered list with one list item to get started. This will simply show a recipe name along with a basic badge indicating recipe type, in this case, dessert. Here's the basic styling for our list, available in the course materials along with every other file we edit or add. Angular CLI is not just for creating Angular 2 apps. The CLI can also be used to generate pieces of our app. Navigate to the app folder with cd/source/app and then run ng generate class recipe. This command makes use of the Angular CLI generator and creates a file recipe.ts with a recipe class. Now let's add a recipe to our class so it will appear in our browser. We should continue to take advantage of TypeScript by creating a model for our recipes. For now, we are going to keep our model very simple. A recipe object simply contains a type property which is a string, and a name property, which is also a string. Now in app.component.ts, we can add a recipe of type recipe. We will set it to type dessert and name chocolate cake. Let's see what happens if we do not follow the model. Changing either of these properties to anything other than a string will result in an error, and a very informative one at that. If you've tried this out, change them back now, and the errors will disappear. After saving the file, we check out the results in our browser. Here we see our one recipe with a nice badge designating it as a dessert. Now it's time to make things more interesting. Let's update recipe to an array recipes. We designate its type like so, an array of recipes. Our HTML, of course, will not work now as we are still referencing a single recipe. We need to learn how to work with structural directives now. A structural directive changes the DOM layout by adding or removing DOM elements. In our case, we will be adding a DOM element, specifically an li, for each recipe in our recipes array. To accomplish this, we will use the ng4 directive. We only need to make one small change to our template by adding the following. The asterisk here is simply syntactic sugar, which Angular replaces with a template. All you need to remember, though, is that anytime you see an asterisk preceding a directive, you are dealing with a structural directive which can alter the DOM. Let recipe of recipes simply says to refer to each object in the recipes array as recipe. We can keep our references to recipe.name and recipe.type the same and simply save this file to see our changes. Now we have a nice list of recipes. Let's make the recipe type more clear at first glance by adding the appropriate class dynamically through the use of ngClass. We will pass a function to ngClass which returns a class name based on recipe type. Here are our basic styles. And here is the function within our component class. Note that we continue to make use of typings. If we return a number rather than a string, an error will be thrown to alert us that we are returning the wrong type. Checking out the results in the browser, we see our dynamic badge colors. In this video, we learned how to work with structural directives as well as class bindings in order to make our view more dynamic. We will now see a list item for each object in the recipes array, and each list item's badge will be colored based on recipe type. We also consistently made use of TypeScript typings in order to ensure we were using the correct data types throughout our component. In the next video, we will take a look at adding services to our app so that we can begin pulling recipe data through service calls rather than hard-coding it in our component class. Our recipe data is currently hard-coded in our app component. This is obviously not where we want this data to reside. Instead, we should create a service which we can use to access this data throughout our app. We will begin by adding the Angular in-memory web API to our app and configuring it with mock recipe data. We will then add a service to our component with add, delete, get, query, and update methods. Our Angular CLI project did not come with Angular in-memory web API as a default dependency. You may remember working with this library earlier in the course to mock up API endpoints. We will be making use of the in-memory web API once again, so you'll need to install it using npm. I recommend simply adding it to your package.json. Make sure you set the version to 0.1.13. To install this new dependency, simply open your terminal to your project directory and run npm install. You are going to see several npm warnings about peer dependencies. Do not worry about these. They will not hinder your ability to move forward with the project. They are warnings, not errors. We are ready to import Angular in-memory web API now, so we have access to it throughout our project. Open app.module.ts and import this library like so. You may remember that we also need to configure in-memory web API module by calling for_root on it and passing our mock data. We do this here. Recipes data does not yet exist, so we need to create that next. Create a file called recipe-data.ts within the app folder and add the following code to it. This should look familiar, as we set up a similar mock data file in a previous section. Note the ID field that we've added to each of our recipe objects. We currently see an error message. Thankfully, this message is quite informative. Our recipe class does not currently have an ID property. Let's jump over to recipe.ts to fix this. Here's the simple update to our recipe class, which will fix the error we just noticed. We just need to add an ID property of type string to our class definition. Save this file and note that recipe-data.ts is now happy. We will now add a recipe service, which will be able to access this data. We will be using the Angular CLI to generate our service. With one command, our service file will be created with a basic structure in place. A test spec will also be created. We will be writing our tests in a future video. Make sure you're in the recipes directory and run the following command to generate a recipe service. ng g service recipe. G is short for generate, and this command will generate a service named recipe. Let's now take a look at the files which were generated. We see here that our service has been created with the injectable decorator already imported and set. We obviously have much more to add to this file, but at least the basics are already in place. Let's take a quick look at the spec file as well. The spec file is created with basic imports and configurations. There is also one test already written, which simply tests that the recipe service exists. We will focus on further testing in a future video. Let's now return to our services and add the methods which we will use to access our recipe data. Let's walk through our recipe service, which is, of course, available in the course materials. First, we import the HTTP modules we will need, including headers, HTTP, request options, and response. We also import observable from RxJS, as we will be working with observables rather than promises. We set our mock API endpoint to /API/recipes. And then we remember to declare our private HTTP instance with _HTTP within the constructor. Now let's walk through each of the methods we have added to this service. Our app is a basic CRUD application. CRUD standing for create, read, update, delete. Our create method is called add, and we have two read methods, get to get one recipe and query to get all recipes. We also have both an update and delete method. Our add method takes a recipe object, sets options, and passes the recipe and options to a http.post. The delete method takes an ID of type string and passes it to an http delete, which uses interpolation to call /API/recipes/ID. To get a particular recipe, we make an http.get call with the recipe's ID passed at the end of the URL. To get all recipes, we simply call http.get on our recipe's URL. Finally, to update, we make a call that looks very similar to our add method, but we append the ID to the end of the URL because we are updating an existing recipe. In this video, we will be working with query and delete. We will work with the remaining methods in future videos. In order to work with observables, we will need several operators from the RxJS library. This is a large library, so instead of importing it in its entirety, we will be grabbing just the operators we need, like so. Create a file called rxjsoperators.ts and add the following imports. Now we will simply need to reference this file from our app component in order to have access to these operators. In our app component, we import rxjs-operators as well as our recipe service. We also must remember to add a providers array and declare recipe service within it. We then declare a private instance of recipe service in our constructor and use it to get all recipes through the services query method. No more hard-coded data in our component. We take advantage of the ng-on-init lifecycle hook so that our recipes are loaded when this component loads. We also add a delete recipe method, which after successful call filters the recipe we deleted out of the recipes array by checking for the ID passed in. Let's add a click handler to our template, which we'll call this delete method now. We add a button to our UI with an event binding to the click event. When this button is clicked, this component's delete recipe method is called with the recipe's ID passed in. Let's test out this new functionality in our browser. Other than the new X button, our UI looks the same as in the previous video, but now our app is loading data through HTTP calls rather than from a hard-coded array. When we click on an X, the corresponding recipe is deleted. In the next video, we will learn how to work with Angular 2 forms, and we'll use this knowledge in order to add the ability to update existing recipes and add new recipes to our app. We can now see a list of recipes, but would like to be able to add recipes to this list as well as update existing recipes. We should also work on improving the overall look of our UI. We will begin this section by adding Angular Material to our app in order to improve the styling. We will also add material design icons to our application to further improve the look of the UI. Finally, we will learn how to work with forms in Angular 2 and add one to our UI so we can add new recipes. To learn more about material design, visit material.google.com. This site does a great job of explaining the design principles behind material design. If you've ever used Google Apps and products, you have seen material design before. Get excited because we are about to add this design pattern to our project. We will be adding the Angular Material library to our project, which contains many UI components. You can learn more about this library at material.angular.io. Angular Material 2 is currently in alpha, so many features and components are not yet available. To see a list of currently available components, visit github.com/angular/material2. We will be focusing on buttons, cards, inputs, and icons in this video. To install Angular Material 2, open up a terminal window and navigate to your recipes project directory. Execute the command npm install --save at angular/material to install this library and save a reference to it in package.json. You may notice several npm warnings. Do not be concerned with these. Now that we have installed Angular Material, it's time to import it into our project. Add the following line to app.module.ts. Import material module from angular/material. You should be getting used to these steps as we followed a similar set of steps when we added the in-memory web API module to our app. It's time to add material module to the imports array and call its forRoot method, like so. Navigate to the following folder within Node Modules. At Angular/Material, /core/theming/prebuilt to view the pre-built theme color schemes available. You may also configure your own custom color scheme, but that is beyond the scope of this course. We are going to be using the deep purple amber color scheme. As the comment here states, the top level styles.css file is where we import style files. Add the following import line to the Angular Material Design color scheme we just talked about. At import angular/materials/core/theming/prebuilt/deeppurple-amber.css. Let's now add material design icons to our app. As you can see here, this library contains dozens of awesome icons. Load material design icons into our app simply by adding this line to index.html. That's it. Now let's start working with all the Angular material components we just added. Here is our updated app component template. You'll notice that we replaced the unordered list with an Angular material list made up of material design list items. Note that the MD prefix on all Angular material components stands for material design. We also updated our button to be an MD button. We set its color to worn and used the material design icon's close icon. Let's check out the results in the browser. We notice some improved styling, particularly with our delete buttons. We'll be using more Angular material components soon, but first we need to add our first form to the app. We will be adding a couple basic forms to our app in this and the next video. This will provide us with a solid base of knowledge about Angular 2 forms. However, there is much more to be learned, and I encourage you to continue learning about forms by checking out the detailed documentation available in the Angular 2 docs. With that said, let's add our first form to our app now. Take a quick look at app.module.ts. Notice that we have already imported the forms module in anticipation of eventually needing to add a form to our app. This is a necessary step in order to work with Angular 2 forms. Before adding a form, let's make our recipes more interesting. Obviously, a recipe will need ingredients. Let's create an ingredient class. Feel free to use the Angular CLI generator to create this class, or simply manually create a new file named ingredient.ts within the app folder. Let's establish that an ingredient has three properties: a name, which is of type string, a measurement, again of type string, and an amount, which is a number. Now that we have an ingredient class, let's add it to our recipe class. A class can indeed import another class. So here we import ingredient into the recipe class and set an ingredients property, which is an array of ingredients. While we're here, let's also add an instructions property of type string so that each recipe has step-by-step instructions. We will now update our recipe data to take advantage of these new properties. This updated recipe-data.ts file is available in the course materials, and all recipe data comes from www.recipe.com. We should now make a few changes to our app component class in preparation for adding a form. Let's walk through the changes we've made here. We import the ingredient class as we will need access to it shortly. We hard code both a measurements array and a types array, which determine the options that will appear in select dropdowns in our UI. Note that in a production app, you may want to take the advantage of using enumerables rather than hard coding these values. But for our purpose here, this will work just fine. We also new up a recipe object as new recipe, and in our constructor, we new up an array of ingredients for this new recipe. This ensures that we have a blank recipe object available to modify when we want to use our future form to add a new recipe. You'll notice several new methods have been added to this class as well. First is add ingredient, which simply pushes a blank ingredient object into our new recipes ingredients array. OnSubmit is the method that will be triggered when a user submits our soon-to-be created form. This method calls add on the recipe service, and upon success pushes our new recipe to the recipes array and resets our new recipe variable to a blank recipe object. Our next new method is remove ingredient, which simply uses the index of the ingredient clicked on to remove this ingredient from the ingredients array. Finally, you'll notice something called getDiagnostic. This method is solely for testing purposes. We will use it to display our new recipe object in the UI so we can watch it update live as we make changes to the form. Feel free to remove this method once you feel comfortable with how this portion of our app is working. The time has finally arrived. Let's jump into our template and add a form. One of the first things you'll notice is that we are using even more Angular Material components now. Our form will live inside an MD card component and will include MD inputs as well as an MD text area. Now for our form. Here we declare the method that should be called when this form is submitted, onSubmit, which we just saw. Most of the details of this form should look familiar to anyone who has worked with HTML forms outside of Angular. What is important to focus on is the use of ngModel. This is the quote-unquote magic behind Angular 2 forms. We spoke earlier in this course about two-way data binding and the banana in a box syntax, which you see here. This two-way binding allows values to move between our form in the UI and our class. In this case, the new recipe variable we declared in our class is two-way bound to this form. Let's take a couple minutes to discuss some interesting features of our ingredients portion of the form. We take advantage of some convenient features of ngFor. ngFor has local index, first, and last properties, which refer respectively to the index of the current item and whether this item is the first or last in the iterable. We take advantage of these properties. After the last ingredient, we append a button to add a new ingredient. For each ingredient other than the first, we append a button to remove that ingredient. We do not display this button for the first ingredient, as we assume every recipe needs at least one ingredient. I certainly would not be excited to eat something with 0 ingredients. You'll also notice some interesting syntax within the name attributes. This simply ensures that the name attribute of each input is bound to the correct index. Otherwise, as you added ingredients, the name attribute would always refer to the current index. Here we have our updated UI, which now includes a form for adding new recipes. This form resides within a material design card and includes material design icons and inputs. Let's add a sample recipe using this form to test out its functionality. We'll add a chicken salad recipe with a fake set of instructions for now. We'll say it requires 1 whole chicken, and we'll test out our add ingredient method by adding, say, 3 teaspoons of salt. Let's add our recipe now. You should have noticed while we were adding that recipe that our diagnostic object was updating in real time, and after successfully adding the recipe, it reset to an empty object. And check it out here, our recipe was successfully added. We covered much in this video. We learned how to add Angular Material and Material Design icons to our application. We also updated our app to contain more interesting data. Finally, we added a form to our app and used it to add new recipes to our existing list of recipes. In the next video, we will be adding routing to our app so that we can view and edit the details of individual recipes. We can see a list of recipes and add new recipes to this list using a form. We now want to add the ability to click on each recipe and be routed to that recipe's details. We also want to be able to edit each recipe's details. We will begin this section by adding the routing module and setting up basic routing. We will then learn how to work with URL parameters in order to route to specific recipes. We will be adding basic routing to our app in this video. For further learning about the Angular 2 router, I encourage you to check out the Routing and Navigation section of the Angular 2 docs. Now that we are adding routing, our app is bound to grow beyond a single app component. Multiple components will now need access to our recipe service. We should, therefore, remove recipe service from the app component providers array and instead add it to the providers array within app.module.ts. This will provide us access to the recipe service singleton throughout our application. While we are in our app module, we should also make updates to handle routing. First, we need to import the router module from Angular/router. You should know what's coming next by now. We need to configure router modules for route method. Let's walk through our settings here. First, we are saying that our route path should redirect to /recipes. We notice that the recipes component will be used for the /recipes path. We then notice that we also have a /recipes/:ID path. :ID will be replaced by the recipe ID, and this path will trigger the recipe detail component, which we will build shortly. We must remember to import and declare these new recipe-related components. Now it's time to add these components to our app. First, let's rename each of our app component files to recipes component to be more descriptive about this component's actual purpose. Remember to update the metadata within recipes component.ts accordingly. Next, we add a very simple app component. All this component does is handle routing. The router will replace router outlet in the UI with whichever component should be displayed based on the route. So, for example, navigating to /recipes will mean that the recipes component is placed here. Likewise, navigating to the root route will redirect to /recipes and again display the recipes component. Navigating to a specific recipe through /recipes/1, for example, will display the recipe detail component for that specific ID. We don't want to have to type a URL in to navigate to specific recipes. Let's add a hyperlink to each recipe's name within our recipes list like so. This syntax resolves to a URL of /recipes/ID just as we wanted. And clicking these links will now take us to the recipe detail view for each recipe. We need to add one more import to our RxJS operators, switch map, which we will use shortly. This is our newly created recipe detail component. Much of this component should look familiar, and indeed shares code with our recipes component. It may make sense to build out a recipe form component, which handles this shared functionality and can be reused throughout the app. However, I leave this as an exercise for you. We will be focusing on routing here. Note that we import activated route, params, and location, which are all necessary to handle routing with params. We then instantiate route and location in our constructor. Most interesting is our ng-on-init lifecycle hook. Our route params are actually an observable, so we now use switch map to grab our ID from these params. We then pass this ID to recipe services get method, which retrieves a recipe by ID. One final note about this file. The onSubmit method now triggers an update of an existing recipe rather than adding a new recipe. Let's take a quick look at our template now. Our template simply displays the details of our recipe, and below these details provides a form for updating the recipe. We also have a back button, which navigates back to our recipes list by using the locations back method. Let's check out the results in our browser. We can now navigate to the details of individual recipes, edit the details of these recipes, and navigate back to the list to see that our changes have been saved. We have reached the end of building an Angular 2 app and now have a solid grasp of how to build powerful applications with Angular 2. We learned about structural directives and class bindings, dove deeper into services, built our first forms, and added routing to our application. We were also introduced to powerful tools and libraries such as the Angular CLI and Angular Material. In the next section, we will be learning how to inject D3 into an Angular 2 app. Welcome to the section of combining D3 and Angular 2, real-time data, and D3 in Angular 2, where we'll add an Express server with Socketio functionality to an Angular CLI-based app to get real-time data. We will begin by discussing our Node.js, specifically Express server. We will then learn how to import D3 into our Angular 2 app. Finally, we will learn how to use D3 to display data in real time. In this first video, we will walk through our basic Express server. We will begin by adding a Node.js server to our Angular CLI-based app, more specifically an Express server. Next, we will learn how to connect to the Twitter streaming API to pull tweet data into our app in real time. Finally, we will add Socketio to our app so that we can stream data from our server to our client Angular 2 app. The app we will be building in this volume was created through the Angular CLI, which we have used previously. I also added an Express server with some exciting functionality to this app. Please fork and clone this project's GitHub repo at github.com/matt-dionis/realtime-angular2 and follow the installation instructions found there. You will need to create a Twitter developer account and then create a basic Twitter app in order to get consumer and access token keys and secrets. Don't worry, this is all free and should only take you a few minutes. Once you have your keys and secrets, simply replace the placeholders found here in server.js. In a production-ready app, you would move these values out of this file into environment variables, but for our local dev purposes, this setup will work just fine. You'll notice in this file that we require Express as well as Twitter. Twitter is simply an NPM library which makes working with the Twitter API easier. Express is a Node.js framework which you can learn more about at expressjs.com. Let's walk through the interesting code found in server.js that's relevant to our real-time data stream. Here we are simply saying that when a GET request is sent to /stream, we should call the Twitter streaming API and track the hashtag JavaScript. Whenever tweets for this term appear in Twitter, Socketio will emit a tweet event with the full tweet object passed back. Soon, we will once again use Socketio, this time client-side, to listen for and react to this tweet event. If you would like to learn more about Socketio, simply visit socket.io. So now that we understand a little more about what our basic Express server is doing, let's test it out. To build and run our app, open a terminal, navigate to the project's root directory, and simply run npm run serve d3.js-build. This will build and serve our application. Now open localhost:3000 in a browser. You should see AppWorks displayed. Next, we will need to send a GET request to localhost:3000/stream. For this, I recommend a tool called Postman, which you can download from getpostman.com. Once you have Postman, you can send a simple GET request like so. Now we need to head back over to our terminal to see the results. And there you have it, a live stream of tweets hitting our server from the Twitter streaming API. We now have a server set up which successfully calls the Twitter streaming API in order to get tweet data in real time. We also have Socketio functionality integrated so our server can send this data to our client Angular 2 app. It's now time to import D3 into our Angular 2 app so we can get one step closer to visualizing real-time data. Now that we have a server pulling real-time data into our app, let's import D3 into our Angular 2 client so that we can eventually visualize this data. We will begin by adding D3 to our project dependencies. Next, we will learn how to import D3 into an Angular 2 component. Finally, we'll use D3 within a component to manipulate the DOM. You will need to execute two commands from within the project's root directory. The first command will install D3, and the second will install D3's TypeScript typings. Run npm install d3 --save to install D3 and save a reference in package.json. I have already installed D3, so I will not rerun this command here. Next, run npm install types-d3-save-dev to install the typings and save a reference in the dev dependencies of package.json. Now that we have installed D3, it's time to import it into a component. We will need to import two new items here. First, we will want to import element ref from Angular-core. Element ref will provide us direct access to the DOM so we can manipulate it with D3. The next import is, you guessed it, D3. We are importing everything from D3 here. One could be more specific once they know exactly which D3 features they are using, but for our purposes, we will import all of D3. Next, in our constructor, we will instantiate a local_element instance, and then use D3 to set a host object. Within our ng-on-init, we call this.build_svg. Build_svg uses D3 to append an SVG to our DOM with the width, height, and background color specified. These lines should look familiar, as this is how we used D3 back in the D3 focused volume of this course. Let's take a look at the results in our browser. And there we have it, the simple 600 by 400 SVG with a blue background that we just appended to our DOM appears. For the first time, we are using D3 in an Angular 2 application. In the next video, we will access our real-time Twitter data so we can use D3 to display tweets in real time. We now have a server pulling real-time data from the Twitter streaming API, as well as an Angular 2 app with access to D3. It's time to combine these powerful features so we can display tweets based on search terms live in our browser. We will begin by adding a server with Socketio functionality to our app. We will then use D3 within our component in order to append tweet text to the DOM each time a new tweet hits our server. We will begin by adding tweet.service.ts to our shared folder. as this service may eventually be shared by multiple components. Let's walk through this service now. The first few imports should look familiar. We import HTTP and response from Angular/HTTP. We also import observable and injectable. Next, you will notice a new import. We import all from Socketio-client. This sublibrary was included in the Socketio library we installed through npm earlier. You'll then notice that we include the @injectable decorator, as we should be doing out of habit for all services we create. We then set the URL and inject HTTP through our constructor. The connect-to-stream method uses Socketio methods to set the URL to listen to. We then specify that we are listening for the tweet event. Remember that our server emits a tweet event each time a new tweet arrives from the Twitter streaming API. We pass the tweet object as an observable and disconnect the socket connection after each event. The other interesting method here is setSearchTerm. This method takes a search term as a parameter and passes it to the endpoint we set up server-side. This endpoint passes the provided term to the Twitter streaming API. The final two methods should look familiar, as we have worked with them before, and they simply handle successful API calls as well as errors. We now need to remember to import our tweet service into app.module.ts and include it in the providers array so that any component within our app will have access to this service singleton. This file should look familiar. We are working with observables, so we can include an rxjs-operators file, which imports the rxjs features we need access to. One final step, and that's to update our app component. First, we need to import both the rxjs operators file as well as our newly created tweet service. Notice that instead of template, we now reference an external template through template URL. We will take a look at this new template in just a minute. We inject tweet service, and along with build SVG, we now call connect to tweet stream in our ng on init. Build SVG is extremely simple for now and simply appends a div to the DOM. This method will become more complex in future videos. Connect to tweet stream calls connect to stream from our tweet service. Remember that this method is listening for tweet events sent through Socketio. When one of these events is triggered, this method uses D3 to append a paragraph element to the DOM with the new tweet set as the HTML. SetSearchTerm calls the tweet service method of the same name to set which term the Twitter streaming API is tracking. Let's take a quick look at our template now. Our template is very simple. It simply contains an input element which is two-way data bound to the term property. This property's value is passed to the setSearchTerm method, which we just looked at. Once the search button is clicked, the Twitter streaming API will allow us to track this term, and our app will display each new tweet containing this term in real time. Let's test it out in our browser. Make sure your app is running by executing npm run serve-build in your terminal. You should then see this simple UI. Let's search for tweets containing the term JavaScript and see what we get. This is a fairly popular term, so after a few seconds you should begin to see tweets. We are using Angular 2 and D3 tied to an Express server with Socketio to display tweets containing the term JavaScript in real time. Now that's pretty awesome. We have learned much in this section, including setting up a basic Express server with Socketio and Twitter streaming API functionality, adding D3 to an Angular project, using D3 to add elements to the DOM based on real-time data. In the next section, we will begin building D3-based Angular 2 components, which will visualize Twitter data. Welcome to the section of combining D3 and Angular 2, creating D3 components, where we will be building several flexible Angular 2 components, two of which will make use of D3. First, we will make use of the input decorator while building a tweet component. We will then begin using D3 as we build a scatterplot component. We will continue to use D3 as we build a map component. Finally, we will add some basic interactivity and animations. In this first video, we will create a tweet component. We will begin by adding a tweet class and filtering our data on the server to match the structure of this class. Next, we will add a tweet component to our Angular 2 app. We will then use the input decorator to provide data to our tweet component. Finally, we will use Angular Material to improve our app's UI. We get a lot of information back from the Twitter API for each tweet, but we only need a small portion of this data. Within the shared folder, add the following new class in a new file, tweet.ts. We are only concerned with the following fields for our purposes: created at, text, username, followers count, following count, statuses count, profile image URL, and coordinates. We now have a predictable data structure we can rely on in our app whenever referencing a tweet. Now we will need to filter the data on our server to match this format. Open up server.js. Instead of simply emitting the entire tweet through Socket.io, we will now filter the data object down first. In cases where there is no location data, we will simply return an empty array for that field. You see that the data returned from our server now matches our tweet class exactly. Now that we can depend on this predictable tweet structure, let's begin using it in our app. Within the app directory of our project, create a tweet component directory and add a TS, HTML, and CSS file to this folder. Let's begin by taking a look at our HTML template. This is a pretty simple template. We are using ng4 to append elements to the DOM for each tweet. We use interpolation to display data such as the tweet text, followers count, following count. We also make use of a data pipe, which formats our created at property. You'll also notice interpolation within the href, which allows us to link back to the Twitter page of the user responsible for each tweet. Further down, we bind the profile image URL to a source attribute so we can display the user's profile image. Finally, we make use of ngIf to display geographic coordinates when available. Let's hop on over to the TypeScript file next to see what our tweet component class looks like. Our TypeScript file is very simple. We import a couple needed features from Angular core and also make sure to import the tweet class. We set the selector, template URL, and style URLs properly. We then make use of the input decorator on our tweets property. We declare that tweets will be an array of objects matching the tweet class we recently created. Input tells our component to expect these tweets to be an input of this component. In other words, you can pass an array of tweets to this component and it will know how to properly display them. So how do we pass tweets in as an input? We are about to find out. Before we forget, let's add tweet component to our app.module.ts like so. Open app.component.html and notice the last line of this template. We've added a tweet component. The square brackets say to bind the tweets array to the tweets attribute of our component, which we just saw was the input of tweet component. We are now passing tweets to a custom component which, based on the HTML template, knows how to format and display them. Before checking out the results in our browser, let's use Angular Material to ensure our UI is aesthetically pleasing. Note, adding Angular Material involves installing the library with npm and adding the dependency to app.module.ts. If you do not remember how to do this, please reference the detailed instructions in Volume 2 of this course. After adding Angular Material to our project, We updated the tweet component template to the following. Each tweet is now contained within an MD-card. We are also now limiting the number of tweets we display to the most recent 10 through the use of index within this ngIf. Open up the terminal to your project directory and run npm run serve-build to build and serve the application. Then navigate to localhost 3000 in your browser to see the results. Search for any word or phrase you like and watch the related tweets stream in real time. Note that only the most recent 10 tweets are shown. We now have a tweet component which handles displaying information for each tweet that arrives from our real-time streaming API. It's now time to begin using D3 as we build a scatterplot component. Now that we have a predictable tweet object being returned from our server, let's use this data along with D3 to visualize our incoming tweets through a scatterplot. First, we'll set up our host SVG element and establish height, width, margins, and scales. We will then use our scales in order to create axes for our scatterplot. Finally, we will populate our scatterplot with data points as we receive tweets from the API. Let's preemptively add scatterplot component to our app.module.ts like so. We need to add one more class to our shared folder, Twitter state. Twitter state is simply an object which contains a tweets array. The reason for this is that we will soon be using a lifecycle hook called ngOnChanges to detect new tweets arriving into our scatterplot. If we relied on the tweets array, we would never see any updates as the array would grow, but would always reference the same original array. Instead, we will be using Twitter state as our input and updating this object every time new tweets arrive so that ngOnChanges is indeed triggered. Create a new directory within the app directory called scatterplot component and include TS, HTML, and CSS files. Open up the TypeScript file. You'll notice the typical imports for a D3 component, including the D3 library, as well as element ref. We also import the tweet class, as we will be working with tweets in this component. This class is where the interesting code resides. Let's begin to slowly walk through it. You'll notice, as we just discussed, that Twitter state is our input. Next, we are simply declaring all the properties we will need, including dimensions, SVG, margin, scales, and axes. Within our constructor, we simply set up our host element. ngOnChanges is what is triggered anytime our input Twitter state changes. In other words, whenever a new tweet arrives, this function will be called. Let's walk through the first two functions called each time a new tweet arrives: setup and build SVG. The setup function establishes margins and then uses the width of our element with ID scatterplot to determine width and height. We then use D3 and set our X, Y, and Z scales to linear scale. For X and Y, we predictably use the width and height to set our range. What is Z, you may ask? Well, Z will be used to determine the radius of our dots on the scatterplot. We set the range from 2 to 15, which will be the pixel range of our radius. Next, build SVG uses height, width, and margin to build our SVG element, which our scatterplot will inhabit. Next, let's take a look at our axes. Draw x-axis passes our x scale to D3.axisBottom, which sets the axis to the bottom. We then declare the number of ticks as well as tick padding. We append a G element to the bottom of our SVG and call x-axis on it. We also append and style the text. In our case, the x-axis will track Twitter followers. The y-axis is very similar to the x-axis. We are simply placing it to the left and labeling it as following, as it will track the number of people each Twitter user plotted is following. Scrolling further down, we see several getMax functions, which simply determine the max value for followers count, following counts, and statuses counts. We will soon use these functions within the domain function of our scale. Scrolling down even further, we arrive at the populate function. We first check to ensure that there are tweets available. We do so because ng on changes will be triggered on page load, but we won't yet have any tweets. We don't want any logic to run on tweets when they don't yet exist. This function simply uses the getMax functions, which we just discussed, to set the domain of our scales. We then append a blue circle with the proper position and radius to our scatterplot based on what our scales return. Let's add the scatterplot component to our app component next. Here you see we've added our scatterplot component and passed Twitter state in as the input. You will also notice a change to tweet component as it now accepts Twitter state as an input rather than a tweets array. I have included an updated app.component.ts, app.component.html, and tweet.component.ts in the course materials for this section. I encourage you to check them out for the small changes required with this update to use Twitter state. Let's check out our scatterplot in the browser. Simply run npm run serve-build in your terminal, as before, to kick things off. Search for the term of your choice and see the results stream in. We can determine a few things about each tweet, namely how influential the tweeter may be based on their followers to following ratio. The most influential would be down here in the lower right. We can also see how prolific or quiet a tweeter is based on the radius of each dot. Let's say we move on and add a new component, a map component, next. We now have a component which shows a stream of the most recent 10 tweets, as well as a component which shows a scatterplot of data related to tweeters. Now let's add a map to plot any location-enabled tweets. First, we will add a map data endpoint to our server to return a GeoJSON object for US states. We will then use D3 to set up a blank map within our new component. Finally, we will plot dots on this map based on the location of certain tweets. We aim to render a map of the United States with state boundaries shown. For this purpose, I found a US states JSON file, which I've included in the course materials. Add this file to the node server directory of your project as us-states.json. Now we need to add an endpoint to server.js so that this file is sent to our client when requested. Within server.js, we need to make two simple updates. First, we require our JSON file and set it to the map data variable. Then, we add an endpoint. When a GET request is sent to /mapdata, we will return the mapdata JSON file. Now we need to add a service so that our client-side app can hit this endpoint. Within the shared folder of the client-side app, add a map.service.ts file with the following code. This code should all look familiar from setting up services earlier in this course. The getMapData method simply returns the GeoJSON object. Don't forget to add mapService to the providers array of app.module.ts as well. Create a map component directory with TS, HTML, and CSS files. We will be focusing on the TypeScript file to build out our map component. First, make note of our imports, element ref and D3 for working with D3, RxJS operators for working with observables, and the map service and tweet class for fetching our map data and working with tweet data. Let's walk through the map component class now. First, you'll notice we declare each property we'll be working with, including the Twitter state input. This should all look very familiar after building out our scatterplot component in a very similar fashion. Next, note that in the constructor, we set our host D3 element, then we get our map data and set up and build our SVG. GetMapData calls our newly created map service to get our GeoJSON data of US states. This triggers a call to the setMap method, which sets the projection, draws the path, and fills each state with a light gray color. For a refresher on creating maps with D3, refer to Volume 1 of this course. Setup and build SVG are then called, which should look very familiar and straightforward, as they mimic what methods of the same names do in our scatterplot component. Now let's take a look at our ngOnChanges method. Note that we once again check that there are tweets available, as we want to avoid triggering our updateDots method on page load when there are not yet any tweets. UpdateDots loops through our tweets as they arrive and pushes any coordinates available into a points array. We then use D3 to append a 4-pixel radius blue dot to the map at the appropriate location. Let's add our newly created map component to our app component template now. Add the map component to app component like so, and make the following CSS update to app component as well. These CSS styles will position our scatterplot and map nicely next to each other. Let's take a look at the results in our browser. Execute npm run serve-build and search for any word or phrase. A note here, a very small number of tweets actually contain geographic coordinates. I tend to search for something location specific, such as weather events, for example, snow. Eventually, you should see a few dots appear on the map. Another note, searching for common words or phrases will eventually lead to a 420 error on the server. This is a rate limiting error from the Twitter API. Basically, just wait a few minutes and try again. Strategies to deal with rate limiting are beyond the scope of this course. I have a nice data dashboard built out to display info about tweets in real time. Next, let's improve this dashboard by adding interactivity and some basic animations. We now have an awesome real-time data dashboard built out with D3 and Angular 2. Let's wrap things up by adding some basic interactivity, as well as briefly introducing Angular 2 animations. First, we will add basic tooltips to the data points on both our D3 components. We will then add click handlers to these same data points. Finally, we will add our first Angular 2 animation to the tweet component. Adding a basic tooltip to each of our data points is very simple. Simply append a title to each circle on the scatterplot, as well as to each circle on the map. We then use an arrow function to return the data details we are interested in. For the scatterplot, we'd like to see the followers count, following count, and statuses count. For the map, we would like to see the coordinates. I encourage you to take this exercise a step further and use the knowledge gained in the D3 section of this course to add custom style tooltips. Let's check out the results of adding these titles in our browser now. To test out features like tooltips and click handlers, I encourage you to enter somewhat less popular words or phrases. This way the dashboard is not updating too fast for you to hover and click. Let's try the word JavaScript. And here are the tooltips we just added. Let's take this a step further and add a click handler so that we can visit a specific Twitter account when clicking on the corresponding dot in our dashboard. Adding a click handler to each data point is easy as well. We simply declare that on click of each dot, we want to call window.open with the URL of that tweeter's Twitter page passed in. Let's see this feature in action. And there you have it. Not only do we get further information on hover, we can now jump right to a tweeter's Twitter page with one click. Next up, let's take a quick look at Angular 2 animations. Angular 2 animations are very powerful and flexible. A whole course could be written just to cover animations, so we will just briefly introduce them here. The first thing you will notice is all the new features we have imported from Angular Core, including trigger, state, style, transition, and animate. If you glance down to the tweet component class's metadata, you will see each of these features being utilized. We set up animations in the animations array of a component's metadata. We have named this animation fly in out and set this name to the trigger property. We will need to add this trigger to the HTML template shortly. We are taking advantage of two special states in our animation, namely the wildcard and void. These states are very useful for defining entering and leaving animations as elements are added to and removed from the DOM. This becomes especially useful with D3, where we are constantly adding data and removing data from our components. We use transform and animate to slide incoming tweets in from the left and remove outgoing tweets, those outside the most recent 10, out to the right over 600 milliseconds. And here's a quick look at our updated tweet.component.html template, where we declare fly in out as the trigger. Let's now test this new functionality out in our browser. You will notice some improved styling here. On the last slide of this video, I will link to my GitHub account where this project's final code is set up. I encourage you to pull that code down and work with it as you're finishing up this section. You now see each of the tweets sliding in from the left over 600 milliseconds. We now have an interactive, real-time data dashboard which includes Angular 2 animations. I encourage you to think of what we have built as just the beginning and continue adding to it on your own. Again, the final project is available here on my GitHub page.